think you can see that. Now we're ready to go. And if my memory is right, we're in Chapter 1, Systems of Linear Equations, Section 1.1, Introduction to Systems of Linear Equations, and we're on page 9. Top of that page is example 9, and that's where we're starting today. So let me get the screen share set up for the whiteboard, because there are no PowerPoints, and that requires me to do some moving of things around. So if I could get there's my pen. Okay, I need to move this taskbar down here so it's out of the way as much as possible. I'll move this taskbar up here and out of the way so it's as much out of the way as possible. I'm going to scoot you over some too, and me, and we'll move the whiteboard as far to the other way as we can so I have the maximum room to write. Now I don't think you see any of this, you just see a white screen, but I have to move my board around a little bit. So let's get example 9. Here is the system of equations. X sub 2 minus x sub 3 is equal to 0. That's not very much, is it? X sub 1 minus x sub 3, no, that's minus 3x sub 3, is equal to negative 1, and negative x sub 1 plus x sub 2, no, that's plus 3x sub 2. I don't know why I'm not seeing my numbers well. Okay. Plus 3x sub 2 is equal to 1. Okay. Now, that's our system of equations. We're wanting to solve that system. That's all it says to do. Now, so far, what are our rules for solving? Ideally, what we would like to have is in the upper left corner, we'd like to have a variable with a coefficient of 1. We've got a 0 up there now. That doesn't fit our scheme too well. However, we have an equation down here who does have a coefficient of 1. And remember, one of the rules that we can do, they're called the elementary equation operations. Okay, the operations that produce equivalent systems, I guess is what they call it. The first one of those, you can exchange any two rows. So basically all we're going to do is move this row to the top and move that row to the number 2. So again, linear algebra is a lot of writing the same stuff over and over again just to get it to fit the format. So yuck. Okay, so our new system, though it's the same system, equivalent system, would be x sub 1 minus 3 x sub 3 is equal to minus 1. X sub 2 minus x sub 3 is equal to 0, and minus x sub 1 plus 3x sub 2 is equal to 1. Okay, so we got a 1 here, and fortunately we got a 0 right there, which is exactly what we want. but we also want a 0 down here, okay? Because we want it in row echelon form, and this isn't because you have something underneath this leading 1 here. But this is real easy to make become a 0. All you do is do equation 1 plus equation 3, and that's the new equation 3. So let's do that. Equation 1 stays the same. X sub 1 minus 3x sub 3 is equal to minus 1. Oh, here comes James. Let me get him in here. And let me make sure there's nobody else waiting. Nope, we got him. Okay, so let me mark James here. All right, 2 out of 3. Hopefully, Jesus will make it 2. All right. James, we're doing example 9 on page 9 in chapter 1, Systems of Linear Equations, section 1.1, Introduction to Systems of Linear Equations. And we went from our original system here, but because we wanted a 1 up here in the top, the variable with the coefficient of 1, we exchanged the first 2 rows and got this one. That's a legitimate operation to do. Then we wanted zeros below it. We got a 0 below it here. We want a 0 here. What we're going to do is add equation 1 to equation 3 to give us a new equation 3. So I was writing down equation 1, not changing that. That stays the same. Like I said, one of the joys of linear algebra is writing the same stuff over and over again. Okay, so here we go. We're not changing equation 2 either. So that becomes x sub 2 minus x sub 3. And that's equal to 0. But the new equation 3 that you get from adding equation 1 to equation 3, which is a legal move, will give you 0 here, 3 x sub 2 here, adding equation 1, to equation 3, yeah. And then adding equation 1 to equation 3 here is a minus 3 x sub 3. And that's equal to, and when you add negative 1 to 1, you get 0. Now, I don't know if you've noticed it yet or not, but the last 2 equations are now exactly multiples of each other. The equation 3 is 3 times equation 2. Which is a good indicator you have an infinite number of solutions. Okay, we'll actually work it out and show you what you get. So what we want is a 1 here, 0 is below it. We got it. We want a 1 as a leading coefficient for this one. Here, we got it. We want a 0 below it. So what we would do is minus 3 times equation 2, add that to equation 3, and that will give you, make this become a 0. So let's do that. So the next step would be leave equation 1 alone. X sub 1 minus 3 x sub 3 is equal to minus 1. X sub 2, we're going to leave that alone too. Minus x sub 3 is equal to 0. And when you multiply negative 3 times the second equation, add it to the third equation, that gives you minus 3x sub 2 plus 3x sub 2, that gives you a 0. Minus 3 times a minus 1 is plus 3x sub 3 minus 3x sub 3, that gives you a 0. So far we got 0 plus 0, and when you add negative 3 times 0, that's 0 plus 0 is equal to 0. Now, question. Is that true? 0 plus 0 is 0? Yes, it's true for every value of x because there's no x's in there. It's always true. It's an identity, never changes. So guess what? You have a row of all zeros at the bottom. What does that indicate? You have something that's always true. That indicates you have infinite number of solutions. If this had come out 0 is equal to 17, that's never true, or even -1, or 0.1. That's still not the same. That would be no solutions. But if you got something that's always true, that indicates you have an infinite number of solutions. Well, what are those? We'll go to the next row up because that tells you nothing, and let's assign a parameter to x of 3. And their favorite parameter of all time is let, it seems like they love t's, t equal x of 3. Okay, then this would say x2 minus t is equal to 0, right? That's what that equation tells you. This one right up here. Well, just add t to both sides. That adds a 0, and you get x of 2 is also equal to t. Well, that makes sense because x of t 2 minus x of 3 is 0, and if they're equal to each other, that's also equal to t. Well, let's go to the first equation now. Plug in a t for x of 3. And that tells you, I don't know if I'm going to have room at the bottom or not. Let's try it. X of 1 minus 3t is equal to -1. So let's add 3t to both sides. And that gives you, this goes to 0. Okay. And this produces x of 1 is equal to 3t minus 1. You could say minus 1 plus 3t. I don't care. Okay. So what's your ordered triplet of an answer? Where's my pen? There it is. Okay, there it is. It would be 3t minus 1, comma, t, comma, t. Name a t, any t in the world. How about 0? That would give you -1, 0, 0. Let's see if that works. 0 minus 0 is 0. Yeah, that works. -1, no, I'm sorry, yeah, -1 minus 3 times 0 would be 0 is equal to -1. Yeah, that works. Minus a -1 plus 3 times 0 is 0 will give you 1 is equal to 1. Yeah, that one works. Not just that one. T equal 1. That would be 2, 1, 1. Plug those in, they will work. Put t equal -1. You get -4, -1, -1. That will work. T equal 7. That would be 20, 7, 7. Plug them in. You'll see they always work. Infinite number of solutions. What gives it away? You get something that's always true, an identity. If you got something that's never true, no solution. Something that's always true, you have an infinite number of solutions. If you came up with a value for x of 3, a value for x of 2, a value for x of 1, a unique solution, one and only one solution. Okay. So, they got the same thing we did. 3t minus 1, t, t. All right. Now, they have a little discovery at the very bottom of the page there, and that's asking you to graph some things. Now, obviously on this whiteboard, I don't graph too well. I don't graph on a coordinate system very well, okay? So it's kind of messy, but I think this is something you could probably do. If you were to graph those two lines represented those equations, you would find that y is equal to 1/2 x minus 1. So have a y-intercept of -1 and a slope of 1/2. So it's something like that. Okay. The second one will give you y is equal to 2/3 x minus 3. Y-intercept of -3 and a slope of positive 2/3. Okay. Now, one's a slope of 1/2 and one's 2/3. They're really close to the same slopes, but they are different. And the intercepts are not far apart either, -1 and -3. So they're not too far apart. So you get two lines that are pretty close, but they do cross somewhere. Now it says use Gaussian elimination to solve that system, and they show you how to do it. And it shows you that the point of intersection is x equal 3, y is equal to 1. Okay? And it says to graph the system of equation you obtain at each step in the process. Okay? So if you graph that second equation, x minus 2y, well, that's the one you've already got graphed. Yeah, that was the first one. But the second one is just minus y is equal to -1. So y is equal to 1. That's going to be, y is equal to 1 would be like this. But they'll intersect at the same place at -3, 1. Okay? No, at 3, 1. Okay? If you do the next equation, same first equation, well, I just did it, y is equal to 1, so I don't know. It seems like it's just taking you through all. And the last one, x equal 3, y is equal to 1, yeah. All three of those have the same solution. A unique solution, one solution. So anytime you have a system of equations, you're going to get linear equations. Whoa, here is Jesus. Okay, perfect attendance again today. Way to go, folks. Okay, love to see it. All right. Any questions, issues, comments? Jesus, we just finished example 9 on page 9, and we're just talking about the discovery at the bottom of page 9. And by the way, that discovery, you can see LarsonLinearAlgebra.com for an interactive version of that type of an exercise. So I don't know. To me, that wasn't as good as many of their discoveries are. Homework exercises. Okay, y'all are familiar with this, so I'm not going to go into it. The answers for the odd numbers are in the back of the book. That's why I assign odd number exercises. But if you can't get those answers in the back of the book, then you can go to calcchat.com, a perfectly free website, just like LarsonLinearAlgebra.com is a free website. Calcchat.com is a free website. It's for worked out solutions for those odd number exercises. So if you can't get the answer in the back of the book, you can't figure out how they got it, go to calcchat.com and hopefully you'll be able to figure it out there. If you want an easy way to get to calcchat.com with your phone or pad or something, just do that QR code and you'll get right there immediately. Okay? Now, and probably these exercises. So that's why I assigned the odd number exercises. Any of the odds 1 through 5, all at CalcChat. Any of the either 7 or 9, both at CalcChat. Any of the odds 11 through 23, all at CalcChat. Any of the odds 25 to 29, all at CalcChat. Any of the odds 31 to 35, all at CalcChat. Any of the odds 37 to 55, all at CalcChat. And then they say you might need some graphing utility to do this one. I'll let you determine that. They are messy numbers. That would be 57 or through 61, any of those odds. Okay, if it gets too bogged down, you don't have a software program or graphing utility, just hang it up. Don't sweat it too much. 63 and or 65, both at Calc Chat. Excuse me. I think I'm going to have to get something to wet my whistle. It's been a long time since breakfast, and I've been talking almost nonstop since 8:30. Well, actually before 8:30, my boss called with a problem, and we had to work that out. So anyway, where did I leave off? Either 63 or 65, both at Calc Chat. 67 is an applied problem. That should be at Calc Chat. 69 is a true-false, 3 parts to it. It should be at Calc Chat. And then 71 is sort of an applied problem. It should be at Calc Chat. 73 or 75 should be at Calc Chat. Different looking type problems there. Okay, and this is something that the author does in this book more than he does in any others, and it kind of irritates me. He brings in a brand new way of doing something in the exercises. If it was all that important, bring it up in the text. Don't bring it up in the exercises, but he does. So try to do either 73 or 75. He talks how to do that. So they should be at Calc Chat also. 77 should be at Calc Chat. Any of the odds, 79 to 83, should be at Calc Chat. 75 should be at Calc Chat. 85 should be at Calc Chat. 87 is a writing exercise. You can look at it if you want to. Doesn't matter, or read what they have at Calc Chat. 89 should be at Calc Chat. And then here he's done it again. No, I guess that's fine. It's sort of like the discovery was. So you could do that. 91 should be at Calc Chat. And 93, they say, is a writing exercise. I'll let you decide whether you want to do that. It should be at Calc Chat. All right, that finishes 1.1. Any questions on 1.1? All right. Section 1.1 is on Gaussian elimination, which we've already talked about, but also we're going to now extend it to Gauss-Jordan elimination. One more step, okay? And here we finally introduce a new term, and that's the term of a matrix, okay? The plural for matrix is matrices. X is singular, CES is plural. Okay, so in section 1.1 we introduce Gaussian elimination as a procedure for solving a system of linear equations. In this section we'll study the procedure more thoroughly, beginning with some definition, and the first is that of a matrix. Now, I've asked this question before, and let me make sure. Don't feel bad, tell me the truth. Do you have a book yet? Anybody who does not have a book yet? Oh, have you got it on Cengage? Have you got an ebook? Okay, right. But you can follow what we're doing in class. Is that right? Oh, that's right. You might not be able to see an ebook while you're looking at what I'm doing on the screen. That's true. Yeah. Yeah. Okay. Yeah, I'm not familiar with ebooks, so I sure can't help out with that. So I'll go on and write down some of this stuff. Um, I was going to say, if y'all have got a book you can look at, I won't write it down. We'll just talk about it, but I'll go on and write it down. Uh, that's correct. Yeah, and we just finished that one. We're starting now 1.2, Gaussian elimination and Gauss-Jordan elimination. Okay. And the first sort of subtopic on the page is matrices. And that, okay, now we aren't that far along yet, but we will be soon. Okay, yeah, that's where we are. Okay, so um, now the rest of you, Kara and James, you both have books or access to a book or something. How about it, James? Yes. Oh, okay. So all of you do. So I guess this first one I need to write down anyway. So all that for nothing. Let me clear my screen here. Anyone need this up a little longer? Okay, let's clear it. Okay, here's a definition of a matrix. Okay, now when you use the letters, and basically this is true in a lot of computer programming, in math, and lots of things. The letters I, J, K, L, M, N just about always refer to integers. Okay, if you ever have done any basic programming, I think that's hardwired into the system. Okay, and many of the others, Fortran, it seems like that's sort of hardwired in too. If you want to change it, you can, but most of the time those letters represent integers, and in this case, yes, they certainly do. Okay, so what we're going to start with is if M, if I can find my pen, well, I've got the wrong end of the pen. Okay, if we're starting out with the fact that M and N are positive integers. I have to write slow or the pen does weird things. Now, what we're going to let those M and N stand for are characteristics of a matrix. And this matrix we'll call an M by N matrix. Now that doesn't mean you multiply M times N. That's not what it means. It's like a 2 by 4. Okay, that means it's 2 inches this way, 2 inches this way, 4 inches this way. Okay, a piece of wood that's 2 inches by 4 inches. It's not meaning you want the cross-sectional area, which would be 8 square inches. It is, but who cares? We're talking about a 2 by 4, an M by N matrix. Okay, now what does that mean? It's a rectangular array. I'll write that down too. A rectangular array usually of numbers. Okay, the numbers in the array can be any real numbers. They can be fractions, decimal, positive, negative, zero, fractions, rational, irrational. Now we're not getting into complex numbers. Any real number. The entries are that. The M and N, they're describing this. And what do we mean by that? Well, let me show you. Here is the classic example of a M by N matrix. The first entry they call A11. Okay? Double subscript. The first subscript tells you which row it's in. The second subscript tells you which column it's in. That's the 1-1 position, upper left corner. Okay? The second one would then be A12. Still in the first row, now in the second column. Next would be A13. Same deal, first row, but now third column. And we'll keep going across that way until we get to the last one, which is going to be A sub 1 N, because the M stands for how many rows you've got, N stands for how many columns you got. That's why they have to be positive integers, because you can't have a fraction of a column, okay? They have to be a whole number of columns, okay? So that's the nth one. So you go to the next row, its entry is A21 because it's in the second row, first column. A22, A23, same reasoning, second row, third column, and then we'll just do our dot, dot, dot across here until you get to A2N, if I could get the N to right. This is such a pain. Okay, third row, the first entry would be A31, A32, third row, second column, A33, and we'll dot, dot, dot across until we get to A3N, the third row, nth column. Okay, now rather than writing forever, we'll just dot, dot down here until we get to, how many rows did we have? M rows. So this will be A sub M, that's just a positive integer, 1. This is A sub M 2, A sub M 3, and a dot, dot, dot until you get to the nth row, nth column, A sub mn. So these are dot, dot, dots, these are dot, dot, dots, everywhere a dot, dot, okay, everywhere, okay, whatever you got, dots everywhere. That is a M by N rectangular array. Why rectangular? It has a length, the number of columns you have, it has a width, or however you want to name that. That's a rectangular array. That's a matrix, okay? M and N are integers. Your A's can be any numbers in the world, any real number in the world. Now we call those our entries, okay? Now, if we're talking about a representative entry, we'll call it A sub ij. Now what does that mean? That means go to the, remember i's and j's are always, or most of the time, integers. So go to the positive integers, by the way, too. I like to call them counting numbers, okay? So go to the ith row, ith row, that could be 17 down here, okay? And the jth column, that could be 5, okay? 17th row, 5th column, IAJ, whatever your symbol I. I has to be somewhere between 1 and M, and J has to be somewhere between 1 and N. So we usually throw that in there as well, okay? So an M by N matrix, what it means, M rows, N columns. Now most of the time we represent matrices by capital letters, and to be real clever about it, we would maybe call this one capital A. Why? Because we made all of its entries little a's, okay? If we had made all these little entries little c, we probably call this capital C here. Now to identify it's a matrix, we usually put square brackets around it, okay? Just to say that's a matrix. Or we can refer to that same matrix in real shorthand by saying Aij. Now that looks like there's just one entry, but remember I goes anywhere from 1 to M, J goes anywhere from 1 to N, so that represents your entire matrix. But we put it in the brackets to tell you I'm not just talking about a single entry, I'm talking about the matrix represented by all those entries, A. Now I jumped the gun on that a little bit. They haven't showed you that yet, but it's going to come up soon. Now, because of this, we call the first number, the first subscript here, or here, the row subscript. We call the second one the column subscript, because that's what it tells you, which row you're in and which column you're in. And then, as Jesus was saying, the size of the matrix is, we don't multiply the numbers together, m by n. We just say it's an m by n matrix. M by n matrix. For instance, if it was 3 rows and 2 columns, we would call that a 3 by 2 matrix. And then you know exactly what it looks like. Entry, 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 entry. I'm sorry. Entry, 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 entry. 3 rows, 2 columns. Okay? I was doing a 2 by 3. Okay. Now, let's look at example 1. All right, to clear this? All right. Okay. Too bad if it wasn't. Okay. Each matrix has an indicated size. You tell me. Don't be looking at the book. Here's a matrix. What's the size of that matrix? Anybody? It's just a 1 by 1. 1 row, 1 column. That's all. It's just a single number. That's a little bizarre, but it's true. Okay. Now, here's one. This is also fairly bizarre. What's the size of that matrix? 2 by 2. 2 rows, 2 columns, right? 2 by 2. Now, the interesting thing about it, every entry in it is a 0. We'll later name that to be the 0 2 by 2 matrix. Okay, pretty clever, huh? It's the 2 by 2 matrix with 2 rows, 2 columns, but every entry is a 0. Okay, how about this matrix? Or is this even a matrix? E2 -7 pi √2 4. Is that a matrix? What's your guess? Thought it was an easy question. Why not? Okay, that doesn't matter. Okay, the first two, one only had 1 entry, so it had to be like itself. The second one had all the same entries but in 4 places, but guess what? This is more typical of a matrix. Most of the time they're not all the same. Okay, no reason to expect them to be the same. So yes, this is indeed a matrix. All it's required, those entries have to be real numbers. E's a real number. It's about 2.7 something another. 2's a real number. -7's a real number. Negative, but it's still real. Pi is a real number, irrational, just like E was. It's 3.1415, blah, 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 blah. You know, irrational number. Square root of 2 is an irrational number. 1.414, blah, 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 blah. You know, goes on forever, never repeating a pattern. Okay? It's a real number. 4, of course, is a real number. It's also a counting number. It's also an integer, but it's a real number. All it requires is the entries be real numbers, and they are. Okay. Now they could even be, yes. Okay. We're not going to deal with matrices that have imaginary components. Yes, you can. It's just that this book, I don't think anywhere, deals with imaginary components. It doesn't mean it's not a matrix, but it's not one that we're going to study. Right now we're defining it to be, let me see, they don't even, oh yeah, right. Look at the remark on page 13, the remark in the left margin. The plural of matrix is matrices. We already said that. When each entry in the matrix is a real number, the matrix is a real matrix. Otherwise, unless stated otherwise, assume all matrices in this text are real matrices. That's what I was assuming. Now, just the way they write that would indicate it is still a matrix if they have imaginary components in them, but it won't be a real matrix. It will be a complex matrix. We're only going to deal with real matrices. So that's why I was emphasizing that. No, you can have matrices with complex components, but then they become complex matrices, not real matrices. So we're going to live in the real world. Okay. Now, one common use of matrices is to represent a system of linear equations. Now, I'm going to show you, write down a system of linear equations. Okay, I'll use the one that's in the book. If y'all have got your books, you can see it. Those who don't have the books or it's hard to look at, I'll write it down for you. Okay, if I can get my pen in place. X minus 4y plus 3z is equal to 5. Okay, let's see. Excuse me just one moment. My stomach is giving me fits. Like I said, it's been a long time since breakfast. I hate to do this, but I'm eating in class. Okay. Sorry about that. All I had were goldfish and they are crunchy. I didn't mean to do that. Let me wash them down. Most of the time I try to go downstairs between my classes and just get a little snack, something to make it so my stomach doesn't roar on me by this time of the day. But both of my first two classes, I had tons of questions at the end of the class, and I had almost no time to get anything done. I ran down and got a bag of cold fish, but I didn't have time to eat many of them, so that's sorry, I hate to do that, but I did. Okay, now I can hardly talk because I got goldfish all over my teeth. Here's the second equation. Minus x plus 3y minus z is equal to minus 3. Third equation, 2x minus 4z is equal to 6. Now I'll tell you right off the top, I don't like this system of equations because it's unnecessarily a little more complicated than it needed to be. This third equation here, I'll look at that and say that's the same as x minus 2z is equal to 3. Why write it this way if you could write it simpler? But they wrote it complicated, so it's okay. Same thing. Now, here is that system of equations represented as a matrix. Okay? Represent that as a matrix. Write down the coefficients. 1, minus 4, 3, 5. Okay? Negative 1, 3, negative 1, negative 3. 2, in this case, 0. Be sure you put something in to hold the place. Minus 4, 6. Again, that irritates me because I would write that as 1, 0, minus 2, 3, because there's no reason to write numbers bigger than they need to be. Okay. Now this particular matrix is called an augmented matrix. Now they sort of dig cart before the horse here. Most books would tell you, what is the coefficient matrix of this first one? And that would be the 9 in here. Okay, these right here. This one starts with this and then goes and said this is called the augmented matrix. That doesn't stand for August, that stands for augmented. And then the coefficient matrix would be what I just described. 1, -4, 3, -1, 3, -1, 2, 0, -4. This is called the coefficient matrix. Okay. Now, what does that do for you? Well, if nothing else, it saves you some writing. Because you see, your variables are the same in every equation. You line them up that way, you keep them that way. That helps you keep things in order. So why have them? Okay? Because you know the first column stands for coefficients of x, the second column stands for coefficients of y, the third column stands for coefficients of z, and the fourth column stands for your constants on the right hand side, your equal sign. Now, back when I was in college first taking linear algebra, we used to draw a vertical line down here to let you know these are the coefficients, these are the constants. I've not seen a book in recent years that do that, so evidently they got away from that practice. I'm not sure why, because I thought it was a pretty good thing to do that helped remind me there was a difference between those entries. Okay, but you don't have to have them. So that's called the augmented matrix, that's called the coefficient matrix. Now, if you think about the approved or accepted operations we were doing, we can now do them by rows rather than by equations. Okay? And you're going to be doing the same thing. It just saves yourself not having to write letters down, not having to write equal signs down. Okay? And it's all set up so you can usually remember. So that's exactly what we're going to talk about next, is what these elementary row operations are. This is over on page 14. Okay. Now, again, let me ask, is it all right just to read these and talk about them, or would it be beneficial to you for me to write these down or type them out or whatever? Let me know. Be honest. Do you want to see these written out, or are you okay just hearing me talk about it? And here's one reason I ask this while y'all are mulling an answer. When you get into sort of educational theory, I don't know if that's what you call it or not, but it's true. You remember a small fraction of what you hear. You remember a larger fraction of what you see. Okay? And you typically remember far better anything you do. Okay? So that's why my talking about something sometimes is a lot of blah blah blah. But when you see it done, hopefully the blah blahs take on a little more meaning. But that's why we give homework exercises, because what you do with it, that sticks. That really hangs in there well. So, do you want to see what I'm saying or just hear what I'm saying? That's what it gets down to. Let me know. Oh, okay, so you can see your books now. Okay, so yeah, well then I won't write it out. In the previous section, we studied these three operations that produce the equivalent systems of equations. Now we'll see these are also equivalent matrices, and we call these our elementary row operations. And we're going to be calling them that from now on. And here's what they are. Just like for elementary, well, in fact, they list the equations here, okay, at the top of page 14. And then in the box below that, they name them as elementary row operations for a matrix. So there. The three operations that produce these equivalent systems of equations are exactly the same as the elementary row operations. Exchange any two equations, exchange any two rows. Okay? Multiply a row by a non-zero constant, just like I was suggesting right here. Multiply, oops, I wasn't over my pad. Multiply this equation, this equation by 1/2, or divide by 2, either way you want to call it. That gives you an equivalent equation. Same thing here. Multiply this row by 1/2, or divide this row by 2. That gives you an equivalent row. Okay, so they call these elementary row operations. So exchange any two rows, or multiply or divide, now get this, by any non-zero constant. Don't ever multiply everything in a row by 0, because you lose all meaning whatsoever. What you would get would be 0, 0, 0, 0. Now you've lost all meaning for that row. And certainly don't divide everything in a row by 0, because that's not even defined. So it has to be a non-zero constant, so therefore you can either call it multiplying or dividing. Just depends on which on top, which is on bottom. Okay, so there's the second one. The third one, add a multiple of one row to another row. And that's what we did too. For instance, the next things we would do here was add these two rows together to give you a new second row. So this would be, now that mark there shouldn't be there. Okay, that would give you a 0 minus y plus 2z is equal to 2. That is an equivalent second equation or second row here. Add these two rows together, 0, -1, 2, 2. Okay, it's actually easier to see if you don't have the letters there. They're actually easier to deal with. So those are our elementary row operations. Remember them, use them. We'll be using them the entire course here. Now, although the elementary row operations are relative, oh, and by the way, what you're trying to get to, remember, was row equivalent form. Two matrices are row, okay, I'm sorry, I got to row equivalent form. Two matrices are row equivalent when they are obtained after doing just any of your elementary row operations. We call them row equivalent. So as we're reducing them to simpler and simpler systems, those are equivalent systems as long as we use one of those three operations. Although the elementary row operations are relatively simple to perform, they can involve a lot of arithmetic. Not difficult arithmetic, adding and multiplying and adding, occasionally dividing. That's all. But there's lots of it. So it's really easy to make mistakes. And once you get one mistake in there, it's really hard to find. So be very careful. They show a little technology thing here. I'll let you read that if you want to use some of those products. Let's go on to example 2. Okay, I think we got time to do it. All right. And this is just real simple. So what I'm going to do here is clear the screen. Anyone need that longer? Okay. Now, here's a matrix. 0, 1, 3, 4. -1, 2, 0, 3. 2, -3, 4. 1. That is a matrix. Now let me say something else now before you get too carried away with this and not realize this truth. that doesn't have to represent a system of equations. It can. That could be an excellent thing to represent a system of equations, a matrix, augmented matrix. It doesn't have to. It could just be a matrix without any ties to any system of equations. Matrices don't have to be tied to systems of equations. A lot of what we do, they will be, but some things they won't be at all. Okay. Now, if we were trying to simplify this, just like we did with equations, we usually want a 1 up here. If I could get my pen to show up. Yeah, a 1 right there. There's no easy way to get a 1 there. Certainly a 0 is never going to become a 1 using any of our elementary row operations. So, except exchange two rows. Now this doesn't have a 1 either, but it does have a -1, so it's going to be real easy to change that later. So the first thing we're going to do is exchange these two rows. A good elementary row operation. So that equivalent system would be, now you don't just change that first element, the entire row. So it would be -1, 2, 0, 3, 0, 1, 3, 4, 2, -3, 4, 1. Those are equivalent matrices. Perfectly equivalent. Now let me just suggest to you what would be our next step. They're not doing this to me. I would multiply everything in the top row, the new top row, by -1. So basically make that a plus, make that a minus, and make that a minus. That's an equivalent matrix. Okay? My minus wound up in the 0 more than the 3, but you get the general idea. Next thing I would do is, actually I should have done it before I did that, multiply this top row by a -2, add it to the bottom row, and you wipe out this 2 here. It becomes a 0, but you do that for the other entries as well. That's what you'll wind up doing. Then the next thing you look for, you want a 1 to be right here. You got it already. And then we'll proceed from there. So all they asked was to do what we did to begin with there before I changed signs. Now, here's another matrix. If I can get my pen to show up. Okay. 2, -4, 6, -2. 1, 3, -3, 0. 5, -2, 1, 2. Okay. Now, again, looking ahead, this is way beyond what we're doing now. What we'd love to have a 1 right here. And certainly one way to do it was exchange these two rows. But guess what? That's not totally necessary either, because notice here, every element in this row has a common factor, 2. So we could divide every element in this row by 2. And that would produce 1, -2, 3, -1. And then the rest of them stay the same. 1, 3, -3, 0, and 5, -2, 1, 2. I don't know why my head is clogging up on me, but it is. Let me see if this will help. If I have the ceiling fan on, I get too cool. I turn it off, it gets too hot. It's just sort of right in between uncomfortable temperatures. This was the B part of the problem they had there in the text. Okay? Now, here's the C part. All right. Original matrix 1, 2, minus 4, 3. 0, 3, negative 2, negative 1. 2, 1, 5, negative 2. And by the way, Jesus, notice these matrices all have different numbers in them, so that first observation you had, the first two examples they gave, did have the same numbers in them, but that was just really wildly asymptomatic. That's not what you usually see. Okay. Now, in this one, remember what we usually like to have to get it in what we call row echelon form, which we haven't gotten to yet. We would like to have in that 1 there. We've got it already. We love having a 0 under it. We've got that already. We love to have a 0 down here too. We don't have. We have a 2. But if we multiply the top equation by minus 2, that leading 1, that's why we love having a 1 there, just multiply that by the opposite of this and then add them together, you got it not. So now I drew arrows here. I didn't do here. Here I could have said row 1, used to say equation 1, now it's row 1 divided by 2 is now the new row 1. So here what we're going to say, the new row 3 down here, if I can get my pen to show up, there he is, okay. Negative 2 times row 1 plus row 3 will be the new row 3. Alright, so that means we leave row 1 alone. 1, 2, negative 4, 3. Notice we spend a lot of time in linear algebra writing the same stuff over and over. 0, 3, negative 2, negative 1. We're not using either one of, we're using the top row but not changing it. The second row is just like we wanted it, so we're not changing it, but the third row, that's the one we change. It's negative 2 times the entire row added to the third row. So let's do it a column at a time. Negative 2 times 1 is negative 2 plus 2, 0. That's exactly what we wanted it to be. Negative 2 times 2 is negative 4 plus 1 is negative 3. Negative 2 times negative 4 is positive 8 plus 5, boy, 13, I think. Okay, and negative 2 times 3 is negative 6, minus 2 is minus 8. Now, my brain didn't seem to be working well that time. Let's make sure, yeah, we got it right no matter what. Okay, now, in the book, notice I just did it by arrows here. They actually wrote in the right hand margin. I can't get my pen to show up. Where is it? Come on, pen. There we are. Okay. All right. They said row 1 and row 2. That's how they technically do it with the row in there. Okay. This one I said row 1 divided by 2. They actually say 1/2 of row 1. And they say becomes the new row 1. Most of the time I don't have room to write that last part, so I just put an arrow. And here where I said negative 2 row 1 plus row 3, come on, becomes the new row 3. This drives me nuts. Becomes the new row 3. Okay. They just have the arrow to it. Okay. They actually wrote the row 3 first, minus 2 row 1. It doesn't matter what order you write it. Now, if you go back to example 7 and 1-1, I think we did that last time, not today. You use Gaussian elimination and back substitution to solve a system of linear equations. In this next example, demonstrates the matrix version of Gaussian elimination. The two methods are essentially the same. The basic difference is that with matrices, you do not need to keep up with writing the variables. So that's the big news. Okay, so I'll go clear this out of the way. I don't know if I have time to finish the problem, but let's at least get it started. Here's your linear system of equations, which I hate to do. Okay, x minus 2y plus 3z is equal to 9. I don't remember if that's the same equation we had before. It may have been minus x plus 3y is equal to minus 4. And 2x minus 5y plus 5z is equal to 17. Seems like this is one we have seen before. Okay, now first step, let's write that as an equivalent, write it as an augmented matrix, which would be simply, now you just, only difference you put it in a bracket now. So it's a 1, negative 2, just write the coefficients down, 3, and then write the constants down, 9. Negative 1, 3, and rather than blanks, we put a 0. Negative 4. 2 minus 5 plus 5, 17. That's the augmented matrix. Okay. Now, I'm not going to write the equations down. If you want to, you certainly can. We've got it in this form. Let's use our elementary row operations. Let's keep in mind where we're heading and what we want to happen. We want a 1 right there. We've got it. Thank goodness. We want a 0 here. Okay? All you have to do is add row 1 to row 2. So row 1 plus row 2 is the new row 2. That's what I do rather than having to write all that down. So our next matrix, the row you're using, write it down. Row 1, that leading 1. You want that there. Don't change it. So you have a 1, negative 2, 3, 9. Then do this to row 2. 1 minus 1, 0. Negative 2 plus 3, 1. 3 plus 0, 3. 9 minus 4, 5. Okay. Now, guess what? Let's not write down every step. We did that one. Now let's do this one. What we want is a 0 here. So we'll do a negative 2 times row 1 and add it to row 3. And that becomes the new row 3. So negative 2 times 1, negative 2 plus 2, 0. Exactly what we wanted it to be. Okay. All right. I get aggravated at this system. Negative 2 times negative 2 is positive 4. Minus 5 is minus 1. Negative 2 times 3 is negative 6 plus 5 is minus 1. And negative 2 times 9 is negative 18 plus 17 is a minus 1. Yes? Okay, that's an excellent question. Here's kind of the answer to that. What we're doing is using, remember I made a big point of that leading 1. When you're trying to get the things cleared from that, yes, you always use that one. The next thing we're going to do over here, we're going to use this leading one. Then we'll multiply by that. In fact, this one, all you're going to do is add. You see? So you use the leading ones. It just happened to be a lot of these are in the first row. That always has a leading one. If it doesn't, you put one there. You make one happen. Okay? And then after that, you use this one. After that, you don't have any more. Okay? So it does seem like we're using row 1 a lot, but not always. Okay? And we'll see a little bit later that sometimes we do change row 1. We're not doing it yet, but we are. So the next thing we look for, and I always go back and say this. Let's review. We wanted a 1 there, we got it. We wanted zeros below it, we got them. What's the next thing we want? Go to the second row. We want the first non-zero entry to be a 1. We want it to be a leading 1. We've got it. So what do we want next? Zeros below it. So what do we do? Add row 2 to row 3, and that gives us the new row 3. Okay? So I'm going to come down here and do that step. Okay? First row, we got what we want. We're going to leave it alone for now. Second row, we got what we want so far. We're going to leave it alone for now. Again, you write down so many things at the same time. Next row is the one we're changing. Okay, first, 0 plus 0, of course, is 0. That was easy. And 1 minus 1, that's 0. That's exactly what we wanted it to be. And then what do we have here? 3 minus 1 is 2, and here we have 5 minus 1 is 4. Now, that's not quite in what we called row echelon form. It's close to it. Leading 1 here, zeros below it. Leading 1 here, zeros below it. But they don't have a leading 1 here. How do you make that happen? Divide everything in this row by 2. Now, I'm doing it real shorthand because we're basically out of time, past time, and that gave you a 1 and a 2 here. Now that's in row echelon form. I should have written that all over again. Now it's in row echelon form. And guess what this means? What did this third column stand for? The Z columns. This says Z is equal to 2. Now we put the variables back in when we need them. And this says that y plus 3z, which would be 6, because z is equal to 2, is equal to 5. And this means y is equal to minus 1. Then plug in here. This one says x minus 2 times y, which is plus 2, because minus 2 times minus 1 is plus 2. Then plus 3 times 2 is 6, so it's plus 6 is equal to 9, and that gives us x equal 8. So there we have our one and only unique solution, 8 minus 1, 2. That's your solution. And that's what we got back in 1.12, I think. I'm not sure they solved the problem. Yes, they did. Now, so we wound up, ran a little overtime, but no extra charge today anyway, is this. We'll start with this remark about row echelon form, what echelon means. We'll start from there and go from there. Okay? Now, so we're at bottom of page 15. Homework exercises in this section, which is a fairly long section. I think you can do any of the odds 1 through 5. Those are easy. I think you can do any of either 7 or 9. Those are pretty easy. They're all at Calc Chat if you need to go there. And then start working on 11 through 17. I think you can do those pretty easily. Okay, we'll hold off. Say again? This is page 22. Okay, any of the odds 1 through 5, either 7 or 9, and any of the odds 11 through 17. Stop there. We'll pick up the rest of those next time. Okay, good deal. Any questions? Okay. If no questions, I'm going to stop sharing. I'm absolutely tired of sharing. Okay. And unless there's some more questions, I'm going to end the session. Are there any more? All right. Well, bye-bye. Have a good weekend. Of course, working linear algebra and research papers and calculus and differential equations. That'll make it a great weekend, won't it? Take care. Have fun. Be safe. Bye-bye. Okay, I've got Angelita here. Brianna is here. Matthew's coming in. Christian's here. James is here. Good deal. And Darius is coming in. Labrina is here. I think I've got everybody so far. It should be 7. 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. Now, while y'all are coming in, I was trying to rush and get my PowerPoint set up, and in the process of doing so, I think I brought up the wrong slide. Yeah, I brought up 15. I meant to bring up 16. Okay, let me get out of here. Okay, still just the 7 of you. Let's see if I can get this done while we're waiting. There we are, chapter 16. I was thinking in my head we're doing the lab on 15, but we're in chapter 16. So, okay. All right, unfortunately. Okay. Now, while we're still waiting for others possibly to be coming, are there any questions, concerns, issues before we begin? Okay, I hear none. Here comes one more. Denisha Benson is coming in.
Mr. Fowler,
Yes.
I have a question about the test one.
Right.
I tried, I was looking for it so I could turn it in, but I didn't see the actual test.
Okay, now I don't know what you mean by the actual test. You mean where you find it on Blackboard?
Yeah,
Okay, send it through messages. It doesn't really fit anywhere on the other thing. I guess I could put it there, but I usually send it through message. Do you know how to find messages?
I meant like the actual test. Like I didn't know where the actual test was.
Okay. You want me to pull up Blackboard for just a moment here?
Yes, sir.
Okay. Don't take me. Yuck. Went to the wrong class. Okay. Oh, man. Blackboard is such a pain in the neck at times. It may not even be the neck. I don't know. I don't know my anatomy that well. Okay. All right, here we go. Getting physical science. Out of that. Okay. Now I think what I'll do, let's go back to Zoom. Let's see if anyone else is waiting. No one else waiting so far. So I'm going to share my screen using this. Okay. All right, now I've got to move some things around because they put everything in the way. So I'm going to put my taskbar down here. I'm going to scoot you guys. For right now, I think I'll just leave you close to where you are. Okay, Can everyone see my Blackboard page for physical science, the main page? Content.
Yes, sir.
Okay. Now, I don't put it down here under weekly assignment or activities. I send it, okay, I think someone's trying to come in. Let me get them in here. No, still 8 people. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, don't know where they are. Okay, so I don't put it there. I put it here under messages because it's easy to send from here. So you see the little envelope here, upper right corner. You see, you can't see that hand going around, can you?
Yes, we can.
You can. Okay, that right there is messages. You see when I put the index finger on it, it tells you messages. Okay, I'm going to click on that, and there I have a message from Jackson that I haven't opened it again yet, but there is the one from me attached to test 1 on chapter 14. Now you don't see it here. If you click on this, you see it underlines and sort of has an icon by it, so click on that. Now I've got to move y'all out of the way. You can't see that you're in the way, but Angelita, you're in the way again. Okay, there we go. Then over here you see Physical Science 111 Test 1. Okay, now even though that does have an icon, it doesn't underline, so you have to go to the 3 dots here, and when you click on the 3 dots, it says download original file. And if you click on that, then it comes down here to the lower left corner, and you'll see it downloading, and when it stops downloading, you can click on it there and open it. Is that what you're meaning and looking for?
Yes, sir.
Okay. Does that,
To
yeah.
turn it in, do we just send it like that?
You can send it back as an attachment to a message. You can send it back as an attachment to an email. I've actually had some people do it before. I'm not suggesting this because it's a little harder to deal with. They've actually written out the answers, and that is their message or email. They don't actually send me a copy. If you can do it with that, that makes sure that see, if you get off a line, especially multiple choice, and I'm going down grading and you don't realize you skipped one, all your further answers could be wrong, but you're answering the right question. So I'd like for it to at least have numbers by it or something so I can tell you are on the right same problem that I'm grading. So that's the advantage of sending the actual test back. So I know you are answering that question and you just didn't skip one, and now I don't know which letter that was really representing. So I don't know if that made sense, but yeah, you can send it back to me. And for those of you who bring it into a Word document, and if you want to type your answer on a Word document and send it back as a Word document, that's fine too. If you want to take a picture with your phone or an iPad or something like that, that's fine. Now, taking pictures, remember I warned you, try to get the light coming in obliquely. If you're directly overhead light and you're leaning over it with your iPhone and looking, the odds are you're going to be blocking and shadowing some, and it may make it so it's hard to read. Now it seems like we lost somebody, but maybe they're still trying to get in. Okay, so if you have capability of doing a PDF, I can open PDF files. Now I can't remember if this class or not. It may have been. Somebody sent me something and their suffix was pages rather than, see, that was dot docx, document with an X by it. PDF would be a PDF. Usually your pictures are JPEGs or something like that. But someone sent me something with the suffix was pages. My computer couldn't open it, but it was just one of those things to confirm that you sent it. So I gathered, I think it was the syllabus agreement or something like that that I really didn't have to see, but you said, here's my signed copy. So I said, fine, I'll take your word for it. So it's a signed copy. I just couldn't read it. So please, if you're sending something like that that has a weird suffix, you know what I mean by suffix, dot pages. My computer won't open that. I don't know what that is. That may be something on a Mac. It may be something on uh, some sort of other thing, but my PC will not open that. I had a student last spring, I think it was, he would send me something and the whole file name was just a series of numbers. 5 digits of space, 5 digits of space, 5 digits of space. My computer didn't have a clue of how to open that, and I didn't either. So I had to email him back, say, look, I couldn't open this. Can you send it to me in some other format? Ultimately, he got it in one that I could. So please don't use something too esoteric that I can't handle. So try to get it like that. Otherwise, I'll just email you back and say I can't open this. Can you send it to me in another format? So don't throw anything away. Okay, hang on to it. And it actually has happened that some people said, I thought I sent that to you. Well, I never got it, and it may be because they mistyped my name on the address line and sent it to somebody else and didn't realize that, or you know, Outlook screws things up, and can't deliver sometimes or something. So uh, don't throw anything away until you see a grade in the grade book for it, and then you agree with that grade. Okay?
Mr. Fowler, I
Yeah.
also emailed you my research paper topic
Okay.
and the student acknowledgement form.
Okay. Great. Thank you.
Get an email, so I didn't know if you received
Okay.
that.
Okay. I'll give you my sad, sad song. You hear the violin music in the background. Um, I have been working on a big project. This is not all it, but this is mostly it right here. And I'm trying to get this wrapped up and finished. I need to have it done by the end of the month. And so therefore I'm behind in emails. I'm behind, like here, Jackson sent me something 21 hours ago. I haven't checked this in 21 hours, so I'm behind. So hang on, give me a little bit of time. Hopefully by the time the weekend's over, I'll be finished with that thing and we'll be able to start catching up. And then when I do see it and print it, I email you or send you a message or whatever and say, I've printed this. I'll grade it when I can, or I'll enter it on Blackboard when I can. See, some things don't get graded; they just get acknowledged. So I'll just say I'll note this on the page when I can get around to it. So yeah, thanks for doing it. I'm sorry I'm just running late. Here comes somebody else in. I don't know who it is. Um, Sancho is coming, or is here waiting to get in. Well, this pen seems to have died completely. All right, were there any other questions, issues, problems, concerns before we actually get started today? Yes. Okay, if you're saying something, it's too light, I can't hear it. Yes. Okay, that's because physical science is only taught on the Bessemer campus. Sorry about that. The bookstores don't cover both campuses, they only cover the campus where they operate. So sorry about that. Um, I would email ahead or call ahead to make sure they had the book before I went, but I bet you the Bessemer campus has it. If I could talk, I would say that. Okay, someone just came in and I noted her name, but I got to talking with you and I forgot who it was. Who just came in? Let's see if, say again? Kendra Lewis, I see you. Okay, got it. Got it. All right, that gets us up to 10 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got it. All right. Basically answering questions, clearing the, oh, I hit the wrong one. Let me minimize this. Okay. And I was answering questions on Blackboard. Any other Blackboard questions before I get out of it? All right. If none, what I'm going to do is go back to my sharing and go to Chapter 16, PowerPoint. Okay, and for some reason this used to always come up with whichever slide I left off on. It doesn't do this anymore, so basically I'm just going to have to space through until I get to the slide where we are. We're on motions of the earth, so let's scroll down till we get there. Oops, that was it right there, wasn't it? I think so. Well, I have several marks on the same page. We went over this one, didn't we? I think so. I think we did 7 conspicuous motions. Yeah, we did the helix, didn't we? All right, I don't know that we did revolution, did we? Yeah, that was it. In the book, it doesn't call it revolution, it calls it orbit. And I had left something erased, so I was on the wrong place. Okay. I believe this is where we were. Any questions before? Yeah, we're recording. Okay. I meant to tell you, we finally, believe it or not, got our Screencast-O-Matic back. The business office finally got around to cutting the check, paying the bill. So I am recording on Screencast-O-Matic. So today's class will be out there. Now, when will it be out there? I'm not sure. Let's see, tomorrow's Friday. It depends on how late I'm working on this stuff tonight. If I'm working late and I happen to notice that it's finished uploading, because this is 4.5 hours of stuff, so it takes pretty close. Oh, wait, here's Diana wanting to come in, so let me get her in. Okay. Got Diana here. Okay, so that should have me up to, yeah, 11 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Got it. All right, so sometime either late tonight, more likely tomorrow morning sometime, I will have this class will be recorded out there on the YouTube videos. And you can access those through week 1. Remember, for a lot of the stuff now, the stuff that's the same every week, I just put it in week 1, and on all, the subsequent weeks, I say, I think someone just left the room. Let me make sure. I don't see anyone new here. Whoops, I think someone just came back in. Or tried to, yeah. Oh, Diana hadn't gotten in yet. So let me admit her back. Hopefully she'll make it this time. Okay, I don't see anyone else new, so let me get out of this. So most of the stuff that is good all term, I put in week 1, and then every week I'll say, I'll put up new PowerPoints every week. Whatever we're doing that week, those will be under, when you go to week 3, say, the first thing is the overview. That changes every week. Okay, the next tab under that is something like materials or support, PowerPoint, blah, 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 that kind of stuff. When you get to that, the PowerPoint at the top, those will be every week. I'll put them out there. Okay, but then the thing under there, recorded lectures, that's mostly for online classes. But because this isn't an online class, I have all my recorded lectures are out there at the YouTube playlist. So I send you to the link in YouTube, and you can see them all. Okay, you can pick the ones you want to look at. Okay, now because that's the same every week. Otherwise, I'd be linking every week to the same place. All I do in week 3 will say under recorded lectures, see week 1. See YouTube link in week 1. Under handouts, that's where I put the research paper instructions and my locator card, plus some of the other things. And I'll say, see week 1. Okay, so you go to week 1 and find what you're looking for. I think that's about all. Some of the other classes have other things, but this class, I think that'll be it. But in other words, you'll see it. But it'll say that in there, see week 1. And I'll tell you what to look for in week 1. So that's where this will be when we finally finish it. Like I said, it's going to take a while for it to upload tonight. And once it gets uploaded, then I have to move it to the playlist. And then you can access it. And if I can do that this evening before I go to bed, I will. Otherwise, it'll be in the morning sometime. All right. Any other questions, issues, concerns, problems, anything whatsoever? Okay, I'm going to scoot Brianna over just a little bit. Labrina, I'm sorry. All right. If there are no more questions, here's where we left off before. If you're in the book following this, this is Chapter 16, Earth and Space. We're in 16.2, which is Motions of the Earth. And one of the main motions is our revolution. Okay? Our going around the sun. Okay? That's called revolution. This is the Earth's movement around the sun. Now, our orbit as we go around the sun, the sun's pretty much fixed in place. We're going around it. As we are, that path that we take defines what we call the ecliptic. That's called the ecliptic, that plane that we're in as we go around the sun. We don't do this kind of motion, just going anywhere around. We stay within a fixed plane. And pretty much all the planets are within that fixed plane. It's sort of a fat pancake. It's not super thin, so they're somewhere in there. We're right in the middle because that's how we define it. That's called the ecliptic. So the ecliptic is the apparent motion of the path of the sun. Because you see, if we're going around the sun and that's the ecliptic, then what it looks like to us is that sun is moving along the ecliptic. Of course, it's not moving, we are. So that's why it's the apparent path of the sun through the heavens as seen from Earth. That's the ecliptic. Now, why do they call it ecliptic? Because wherever the sun is viewed from us, if we're here and the sun's out here somewhere, okay, when I'm looking at the sun is blocking everything behind it. It's eclipsing everything behind it. Okay? Now the stuff back here I'll see tonight, okay, because the sun will still be over here. I'll be turned around, so I'll be facing out there. I'll see that stuff. I won't ever see the stuff on the other side of the sun until I move around here, and now the sun's here, and now it's eclipsing the stuff over there. That stuff over there I'll see, maybe early morning, late evening, something like that. I will see the stuff that it was eclipsing a few days ago, but I won't see the stuff that was in, say, the early morning of those few days ago. It'll be eclipsing that. So that's why they call it the ecliptic. Okay. Don't confuse that with elliptic. Okay. We are in an elliptical orbit, not a circular orbit. Now, oops, here comes Jackson. Okay, we're just looking at his, you didn't see it, but I was showing that he had sent me a message I haven't read yet. So Jackson is here, or it's mostly here. My pen quit writing when I was trying to mark him here. Okay. Now, here is an unusual thing for us in the Northern Hemisphere anyway. Our orbit is elliptical, not circular. That means an ellipse a circle has one center, and you're always equidistant from the circle. If that was the case, that would be okay. That's not the case. every planet, in fact, most of the things in the universe, appear to move not in circular orbits, but in elliptical orbits. Now, ellipse has two foci. That's plural for focus. Two foci. The sun's at one, and there's nothing at the other that I know of. It's sort of an imaginary one, but the sun's at one. So sometimes we're out here farther from the sun, and other times we're over here a little closer to the sun. Okay? Because of that, and when I say a little closer and a little further, we are actually, believe it or not, closer to the sun in January than we are in July. And you would think to yourself, why aren't we warmer in January than we are in July? That's because the Earth is also tilted. That tilt affects our temperature way more than our closeness. Okay? Now, we are 2.5 million kilometers closer to the sun in January and 2.5 million kilometers further from the sun in July. Now, 2.5 million kilometers, okay? Multiply that by 0.6. I would say it's about 1.5 million miles. 1.5 million miles closer in January and about 1.5 million miles further away in July. But think about this. Out of 93 million miles, what's 1.5 million? Okay, it's a little bit, not much at all. So that's not enough to affect our temperature greatly. Our tilt, that's what affects our temperature greatly. Okay, so the Earth itself receives about 6% more solar energy in January than it does in July. But the tilt is why we're colder in the winter, colder in January than we are in July. We'll talk about that later. Now, think about the poor people in the southern hemisphere. Think Australia. Think southern Africa. Think South America, southern South America. They are actually closer to the sun in their summer. See, when it's winter up here in the northern hemisphere, it's summer in the southern hemisphere. And when it's summer in the northern hemisphere, it's winter in the southern hemisphere. So not only are they closer, but they're tilted toward the sun. So I would expect, I don't know if this is measurable or not, but I would expect that the summers are a little more extremely hot in the southern hemisphere, and the winters a little extremely cold. Probably not a lot, but just a little bit. Okay? Just because they are closer in their summer and further in their winter. If anything, for us, it moderates the differences in temperature. I don't know if it's enough really to notice. So, I can't move off this screen, so let me click on the screen and now move. This is a greatly exaggerated view of that. Okay? We are not that much closer to the sun than we are, this is in December, than we are in June. It's a lot smaller ellipse. I mean, when I say smaller, it's a lot more circular ellipse. It's not circular, it's still elliptical, but it's just not much out of thing. They've exaggerated this so you can tell. But this is what I meant. See, we in the northern hemisphere, we're tilted away from the sun in December. We're tilted toward the sun in June. So even though we're further away, the tilt here is what makes June, summer, our hot season, and makes winter in December our cold season. It's not how close we are to the sun, it's that tilt. And here's part of the reason. There's actually two things that play together there. You see the sun's radiation. By the way, this is not at all the scale. the sun should be enormously larger, but you see, if you did, you wouldn't be able to tell where the earth was anyway. So they made the sun small. It's not small, so don't ever guess that. But the radiation coming from the sun, see, is hitting directly pretty close to the equator, okay, every season. That's why the equatorial regions, the tropical regions don't vary much in temperature around the year. They just don't, because they're all fairly close to the sun. But we're up here in the what they call the temperate region, and the sun rays coming in here have to go through way more atmosphere before they reach the earth, and then they bounce off pretty easily. These down here, those rays hit directly and they don't bounce off anywhere. Okay, so they get the full brunt of the radiation coming from the sun. Up here, some of it gets deflected and it passes through more atmosphere, so it gets moderated. However, when we're tilted toward the sun, now there's less of an angle there, so we get more direct radiation coming in. So it heats us up more. That's why we get hotter in the summer, colder in the winter. It's not our distance from the sun. Yes.
So my home country is so we only have 2 seasons. We only have wet and dry. Is that because we're always into the sun?
Okay. Let me ask you, what's your home country?
It's called Uganda.
Uganda. Oh, very close to the equator, right?
Yes, sir.
Yeah. Okay. Now, Uganda would be, I think it's just north of the equator, isn't it?
It goes like
Right through it. Okay. Okay. So you see, no matter where you are around here, the sun's rays are coming right at you pretty much. Okay. Now, the wet dry, that's y'all call them monsoons, right? Okay, yeah. And that's what they call in a lot of sub-Saharan Africa and a lot of other places. I believe India has this too. I'm pretty sure that parts of Brazil and other parts of South America that where the equator cuts through are awfully close to. That's pretty much what you get. Rainy seasons, dry seasons, because your temperatures don't really change that much. Is that right? Yeah, I had a student in this class, it's probably a decade or longer ago, who was from Kenya, a neighbor of Uganda, right? Okay, or awfully close if it's not directly a neighbor, but very close. Um, and she was from fairly close to Nairobi, which is pretty close to the equator as well. And she said it just shocked her that the days were longer in the summertime here and shorter in the wintertime. She said, what's wrong with these people here? Because she was used to her whole life, 12 hours of light, 12 hours of darkness year round. And we'll talk about that later. In the temperate regions, and the further north you get, the more extreme that is. Okay? In the tropical regions, anywhere from 23.5 degrees south of the equator to 23.5 degrees north of the equator. Uganda is right near the equator, so it's in there. Very little difference in temperature, very little difference in daylight hours. And that was the second reason I was going to talk about, is that you see in the wintertime, because we're up here, we spend more of our day facing away from the sun, so we have fewer daylight hours. So the sun has less time to warm us up. Whereas in the summertime, more of our day is spent toward the sun, so we get more time to warm up. So there's the second reason. The first reason is the sunlight comes in more directly and less gets deflected in the summer than in the winter. And the second reason reason is we get more daylight hours in the summer and fewer in the winter, so we have longer to warm up and stay warm longer. So those are the two major reasons. Those both come from the tilt of the earth. The distance from the sun, that distance is negligible. Okay. Now, to answer the question about the why you have monsoonal seasons, wet seasons, and dry seasons, that's a question for the climate and weather chapter, which is next to the last one we'll do, and I will not know the answer for that then either. It just has something to do with how the systems um, operate in that part of the world. And I can't really do much better than that. But let me say this: I believe even Cuba, which is just south of Florida, I think they have wet seasons and dry seasons. They're also in the tropics, and why that's the case, I'm not really sure. Here is one guess. Right now, we're in hurricane season, right? Ask the people in Louisiana, they're getting smacked, or they have been smacked. Okay? And the thing is, a lot of the big systems come from east to west that drives our weather. Okay? Now, when is your dry season? Is it this time of year, or is it more in the what we call our winter? Matthew, you still there? Okay. Okay, yeah. And you were probably pretty young when you left, and it didn't matter to you. It was either raining or it wasn't. Okay, okay. Uh, yeah, so it would be interesting to follow that up. In fact, frankly, I would find that a very interesting paper topic. If you're interested in it, that's it. That seems like that would have potential to be a really interesting thing to look into. But if you're not interested in it, don't feel. Oh, you've already turned in your paper anyway. Never mind. Okay. But for anybody else, that might be an interesting topic. Okay. Because I don't know the reason for monsoons. I don't know why some seasons are wet. Because um, here in the U.S., um, in the southern U.S., here where we are here, this to me has been the wettest, one of the wettest years that I can ever remember. I can't remember hardly any time that we have been what I would call a drought condition. And a lot of summers, I was just telling my wife yesterday, I was looking out in the backyard, the side yard. I said, I can't remember any time this time of year, late August, when I could look out and it didn't look like the trees were just suffering like crazy. Like, please give us a break. The leaves all look fresh and green and healthy because they haven't had any drought at all. Our pear tree down right by the road has had more pears on it, the squirrels can't even keep up with it. We hardly ever get a pear because the squirrels get them all when they're green. We have so many pears on that tree, the squirrels can't keep up. I think it killed them because they overate themselves. I don't know. We've canned, put up pear preserves. It's just been a wonderful, wonderful growing season for just about everything because we've had rain, rain, rain. Uh, I'm hoping we're not going to enter a dry season coming up because I love to have the rain. Maybe y'all don't, but I do. But we'll talk about that a little later in this chapter and like I said, chapter 23. Okay. Now, the other two things to note, um, when the sun is at the lowest point in the sky, further south of the equator, which is 23.5 degrees south of the equator, the date it reaches there, that's called the winter solstice. Now, I don't know if you can read that because that block may be in the way, but winter solstice. Now, what that means, SOL, just like solar system, SOL stands for sun. Now, if you were tracking this, it would be pretty boring thing to track, but if you were to go out and track every day at precisely noon, now I'm not talking about clock time noon, I'm talking about the time of day when the sun crosses our local meridian. In other words, it's the highest point it is in the sky. If you mark that for today, and you marked it for tomorrow, and the next day, and the next day, you might want to mark it on a weekly basis. That would give you a little more. You would notice that every time you marked it, it's down just a little bit lower than it was the week before. just a little bit lower than it was the week before. So the sun seems to be dropping in at noon, be a little bit lower in the sky. In June the 21st, it was way up there, and now it's probably down about like that. So it's dropped at noon a little bit in the sky. Okay? Now, as it keeps dropping, this is August, it'll keep dropping in September, it'll keep dropping in October, it'll keep dropping in November, it will keep dropping in December, and there was a time that the ancients, being fairly superstitious and stuff, not that we aren't, but they were, that they were afraid that the sun may keep dropping and never come up again. And that bothered them. So every year, as it would drop and drop and drop, by the way, it's getting colder and colder and colder, and they were afraid it was going to drop and never come up again. But every time around December 21st or so, it stopped dropping. It stood still. Stis means still. The sun, sol, stood still. Solstice. That's what that meant. Okay? And then they had a big party because the sun stopped dropping and started going up again. They were promised another growing season. They partied like crazy. And that's why some of the people, I'll say, that are into things like, I hate to, this is too great a classification, witchcraft and things like this, they'll have a big party around summer solstice. That's because that's from ancient times. That's when the big parties were. And guess what? And this sounds like it may be heretical, but hopefully you don't take it that way. No one really marked on the calendar the date that Jesus was born. I mean, we say it was December 25th, but you know what? December 25th is right in the middle of party time. And I think that what the early Christians did, let's take advantage of the party and make it our party, okay? And then we won't get thrown into jail or lion's den or something like that. We will say everybody else will think we're partying with them. We'll be celebrating the birth of Jesus. Because guess what? The shepherds probably weren't out in the fields at night in the middle of winter time. They would have had their poor old sheep in the warm, wouldn't have them out in the fields. So more than likely he wasn't born on December 25th. But that's when historically we've always celebrated Christmas. So sorry if that burst any bubbles, but it's probably reality. Okay. So the earth moves on around the sun over here, and around March the 20th or 21st, okay, the sun is directly over the equator, directly over it. And that means everywhere as the earth turns, it spins, the sun is, when it's noon, it's directly overhead, directly overhead. It's only directly overhead at 23.5 degrees south here. Not at that, it's awfully close at the equator, but not direct. And 23.5 degrees north, not direct, but that's where it is here. As Earth moves around here, it's directly overhead the equator, exactly smack dab on the equator. Somewhere in Uganda, it's directly overhead on March 21st. We call that day spring equinox. Now, if you wipe out the nox there, it almost looks like the word equal. That's what it means. If you wipe out the equi here and think of nox and think of the German spelling for that, Nacht, that means night. Equal day, equal night, everywhere on the globe. North Pole, South Pole, everywhere. Every day has 12 hours of darkness, 12 hours of light. Everywhere on the spring equinox. Over here on the winter solstice, look up here. Up here at the North Pole, no matter how the Earth spins, it's facing away from the sun. 24 hours of darkness. everywhere in a circle up there called the Arctic Circle. Okay, way away, long way from Uganda. Okay, if any of you are from Norway, you may, in the northern part of Norway or Alaska or somewhere like that, Siberia, you may have been close to experiencing that. 24 hours of darkness here, never rises. Here, 12 hours of darkness, 12 hours of daylight, 12 hours of dark. Okay. As it moves on further along here, and the tilt gets here, now we're 23.5 degrees north is where the direct sun is. And in between here is between the equator and 23.5 degrees north. From here to there is in between 23.5 degrees south to the equator. So it stays in that band year round. Here it's at the northern tropical circle. That's called the Tropic of Cancer. The one over here is the Tropic of Capricorn. 23.5 degrees south is Tropic of Capricorn. 23.5 degrees north is Tropic of Cancer. The sun is always directly overhead year-round somewhere in that band between 23.5 degrees south and 23.5 degrees north. At noon, some day during the year, is directly overhead. Anywhere else, if you're above that, like we are, we're 33 degrees, 23 minutes, and 45 seconds north. We never have the sun directly overhead, but it's awfully close here. Not quite directly overhead, but close to it. Okay? Over here, it's way down. Okay? Way down. Probably only about 30 degrees or something like that. We'll talk about that later. Okay? But this is called the summer solstice because every day from March the 21st or so until June the 21st or 22nd or so, every day the sun goes up a little bit higher at noon, up a little bit higher, up a little bit higher until on June the 21st or 22nd, somewhere around in there, it stops, and after that it starts going down. So again, the sun stopped, solstice. Sun stopped, or still, sun was still, and that's called the summer solstice. Okay? Summer because that's our time of year. Of course, if you're in the southern hemisphere, this is your summer solstice, this is your winter solstice because you're down here. You're facing away from it. And in the summer, and our winter is your summer, you're facing toward the sun. But then as the Earth continues its trip around the sun, it gets back over here and around September the 22nd or 23rd. Coming up in about less than a month now, the sun will be directly overhead the equator that day. Wherever it's spinning on the equator, it'll be directly overhead. And that day, equal night for the whole planet. North Pole, South Pole, anywhere you are, 12 hours of darkness, 12 hours of daylight, okay? And that's the autumnal equinox, equal night. That's the one that comes in the autumn. And then from there, the days keep getting shorter and shorter. The sun keeps going lower and lower in the sky until it stops at the winter solstice and then starts rising again here. This, by the way, winter, this spring, this summer, this autumn. That defines our seasons. Now, of course, you're in the southern hemisphere. This would be summer, fall, autumn, winter, and spring. Exactly opposite of us. All right, any questions about that? And again, this is a greatly exaggerated. The ellipse is off kilter, but they did it for emphatic purposes only. All right, so there's the first, the orbit around the sun, and that splits us into the summer solstice, the winter solstice, the equinoxes. Just making sure I hit all of the important things there. Now, here's the way to look at it in terms of that ecliptic, the path of the sun. our equator is always right there. That's the, because of our tilt, that's the red circle. You see the North Pole is pointed one way, the South Pole is the other way. Our equator is equidistant. However, the sun is on that flat part. That's the ecliptic, where the sun is. And for the half of the year where the sun is below the ecliptic is below the equator, that's the fall and winter season, and in the northern hemisphere. And then when it's above it, that's the spring and summer seasons. Okay. If you got your books, you can look at that and study it. Now, here's some interesting questions here. Example 16.1. Now this gets a little complicated, but hang with me. What is the latitude of an observer who measures the sun's altitude of 38.5 degrees above the southern horizon at noon on the summer solstice? Okay. Now, what is the latitude of that observer? Okay. Now, directly overhead is 90 degrees. The latitude is how far the equator is tilted compared to at your location, how far up from the equator you are. Now, if it's the summer solstice, the sun is 23.5 degrees above that the celestial equator. That's what it means. That's where the sun is, 23.5 degrees above it. If you're another 38.5 degrees above that, if the sun is 38.5 degrees above the southern horizon at noon on the summer solstice, that means that you're 38.5 degrees above the celestial equator. So you add the 23.5 degrees to the 38.5 degrees, and that gives you your 75 degrees north. That's a little awkward to think of it in the way they did it. However, we will be doing this in the lab, and hopefully it'll make a little more sense. That's the only reason I brought it up now. That's the type of thing we will be doing in the lab. Now, another concept applied, they say here, is make a chart to show the time of sunrise and sunset for a month. Calculate the number of daylight and darkness hours. We'll be doing that in the lab too. Well, not exactly. That would have been the first lab, but we didn't do that one. Okay. But does the sunrise change in step with the sunset, or do they change differently? Basically, when the sunrise is getting later in the morning, which it is now, the sunset is getting earlier in the evening, which it is now. Okay? So they are going same pattern, but in opposite directions. Okay. Just, you can do that if you want to. It may be a fun exercise. So let's now turn to rotation and the Earth's axis. All right. The Earth's rotational axis is inclined at, guess what? 23.5 degrees. That's why that showed up as your tropics. That's why it shows up in lots of places. 23.5 degrees from being directly above the plane of the ecliptic. We're 23.5 degrees off of that. Okay? And that determines our seasons. The seasons are determined by that orientation of the rotation axis. The winter solstice, as we saw in the last slide, is when the sun is, when we're tilted as far away from the sun as we can be. The sun has been dropping every day, and it's noontime. They call it the transit across our meridian, dropping every day a little bit until it stops and then starts picking up again. That defines the winter solstice. Opposite is true in the summertime. It gets higher in the sky every day until it reaches stops and then starts going down after that. That's our summer solstice. And on the other ends of the thing there, let's see, is someone come in or someone leave? I don't see anybody else coming in. Okay. Then on the other ends, those are the extremes this way. On the ends this way, those are your equinoxes. There the sun is directly overhead the equator in the spring and in the fall, and those are the days of equal day, equal night, 12-12, day and night, all over the globe, the entire globe. Okay. Now, the celestial equator is the line on the celestial sphere that's directly above the Earth equator. So if we're tilted like this, 23.5 degrees, then our equator is around like this, then the celestial equator will be projection of that outward. Like if you had a light bulb in the middle of the Earth and you had an actual line around the equator, that would form on the celestial sphere the celestial equator. Let's see if we can see that in this slide. No, I can't. Okay. There we go. Yeah, this is the one I was showing you before. Okay, you see we're tilted 23.5 degrees from being straight up. Now remember, this is the ecliptic here. And it looks like to me they have this at an angle, which is a little awkward. They should have had this flat, and I don't think that's flat. They have it at an angle. Okay, meaning the sun is here, the sun's over here, the sun's over here. The sun's always directly above, or from Earth to sun. The sun always follows that path. Here is winter solstice as far south of, because that's when we're tilted away from the sun in the northern hemisphere. So the sun is 23.5 degrees south of the ecliptic then. Summer solstice, the sun is 23.5 degrees north of the celestial equator. Celestial equator is this, our equator projected outward on the celestial sphere. That's the pink line here is the celestial equator. They don't label it, do they? I don't see it on here. That's the celestial equator. The ecliptic is the blue circle here. Okay. The North Star directly above our North Pole. It never moves. Okay. And this is a summer solstice where the ecliptic is as far north of our equator, celestial equator, as it can be. Winter solstice is when it's as far south as it can be, 23.5 degrees south here, 23.5 degrees north here. Autumnal equinox is when they cross, and spring equinox is when they cross again. Autumnal equinox, when they cross, the days are getting shorter, nights are getting longer. They're exactly equal here. Here their days are longer, nights shorter, but not by much. Here the nights are longer, days are shorter, but not by much. But then it expands here and here. Now if you're right on the equator, hey, they're equal day, equal night. That's what equator means. They're awfully close to 12 and 12. Okay. I think we beat that to death. Okay. Any questions on that before we move on? No. Okay. That was really quick. We must have beat it to death. Okay. Wait a minute. I don't feel us spinning. How do we know that we really rotate? Or is this just some scientist coming up with some weird idea and it's got everybody believing it? Well, there's 3 observations they mentioned here that indicate, sure enough, there's a great likelihood the Earth is rotating. Okay? Here's the first one. And I think Galileo was the first one to notice this. He may not have been absolute first, he was one of the earliest. When he was first looking at Jupiter, remember, he improved the telescope so much he could see Jupiter. Jupiter has that great red spot, remember, and it's spinning pretty rapidly, okay? You remember that from the last chapter. Well, he could tell night after night that Jupiter was rotating. There was no reason before that for him to suspect it rotated. Okay, but he could see it. It was rotating. Now they've also measured this, and this is in your book, and it's another evidence, but don't try to do this yourself. There's a certain sunspot on the sun, okay, and different times of months of the year they have photographed that, and sure enough the sun is spinning. You can document that, okay? It's being measured by carefully monitoring the changing position of sunspots. Notice that many of those sunspots are many times larger than the entire planet Earth, okay? That's how big the sun is. And you can see them spinning over time, okay? Well, if the sun's spinning, Jupiter's spinning, all the evidence is that just about everything spins. Why would you think the Earth wouldn't spin? Okay? Evidence number one. Looking at other bodies in our solar system, sure enough, they spin. Now, here is another one. This thing is called a Foucault, I don't know if I'm pronouncing it right, Foucault, I don't know how you pronounce this, pendulum. Now, have any of you ever been to the McWane Science Center? Yes or no? I don't hear anything. Yes. At one time in the past, over in one side, I think the side closest one of the streets there was this huge pendulum that was always going back and forth. I don't know if it's still there now. It seems like the last time I was in there, I didn't see it. Okay? But several years ago, it was there. That was a Foucault pendulum. If you were to hang around there, and usually you don't get to, but if you were to hang around there for several hours and mark where that pendulum was on the floor, you'll see that in time it has moved. It's still going back and forth, but it's slightly moving. Why would that move? Because the Earth is spinning. It's trying to maintain its same path, but the Earth is moving under it. Okay? And this is what they show. I wish sort of we were in class, but I've never done this as a demonstration in class. But you can imagine this. Get one of those laboratory stools that spin. Or those people who haven't been in laboratories and you've been in bars, shame. A bar stool that spins, okay? Any stool that is a spinning, okay? And put an object here, this is called a lever arm or something like that, and put a ball, two balls on it, or a single ball, and it started moving. Then spin the thing. Well, it's moving like this, and then like this, and then like that. That's exactly the pattern that a Foucault pendulum makes. And with it making that, it's just evidence the Earth is spinning. Just like this thing on a spinning lab stool. Okay? It's going different directions. Still going back and forth, but that's cutting a different thing. Same thing. Much slower for the Earth, but it still does it. Then there's one more thing. This is called the Coriolis effect. If you were way up in, say, an aircraft, and this is not going to be a very pleasant picture, but think that you're in one of those bombers that bomb from a high altitude, and you were to drop your bomb. When it went down, if you could see it the whole way and there weren't that many clouds and stuff, you would see that not only does it fall, but it bends. The path bends. And why is that? Because as it's going down, actually the Earth is spinning under it. So it makes it look like the bomb is twisting. It really, believe it or not, is twisting because of the spin of the Earth. That's called the Coriolis effect. And by the way, if anyone has been paying attention to it, who in the world was Foucault? How did he come up with this pendulum? That could be 2 or 3 paper topics. Who was Coriolis? Sounds like a good Italian name to me. How did he come up with this? Who uses this? I've just given one example. You have to account for it when, say, a bomber is dropping a bomb. Otherwise, he drops it, thinking it's going to land on one place, the Earth spins, it lands somewhere else. Whoops, that's our troops. Okay, we don't want that to happen. Let's not get in war anyway, so that wouldn't happen. But that's the Coriolis effect. Now, here's another really practical example of this, and they're experiencing this in Louisiana and Arkansas right now. When you have a low pressure system, air is rushing in, and when it's rushing in, because of the spin of the Earth, it picks up a counterclockwise spin. And that's why hurricanes spin counterclockwise. If you look at the picture of the hurricane, you'll notice the winds are going counterclockwise. That's in the northern hemisphere. If you were in the southern hemisphere and there was a hurricane down there, it would be spinning clockwise. Why? Because you're on the other half of the Earth, and there the deflection is in the opposite direction. On the other hand, high pressure area, which usually doesn't cause storms or things like this, they spin in a clockwise direction. And you look on the weather map and you'll see that happening. Okay? That's the Coriolis effect. Now, just a dumb illustration of why physicists are so crazy, or how crazy they are. When I was a probably junior, senior type time as a college student, one of my physics professors, I had him for 2 classes then, I had him 1 more class in grad school. He was sort of an oddball himself, as this story will illustrate, but he was a honcho. I mean, an international honcho in crystallography. Okay? In fact, he was, if my memory's right, was the editor-in-chief of the main crystallography, international crystallography journal. I mean, that took some chutzpah. I mean, he was up there near the top of his field. Okay? Brilliant physicist. Okay? In that area especially. Well, as that big a honcho in the area of crystallography, and they had meetings probably once every 3 or 4 years somewhere in the world, and they probably moved those around, and it just happened to be one of the years he was the chief editor, they decided to hold their meetings in Rio de Janeiro, Brazil. I don't know if y'all know much about Rio, but Rio sort of prides itself in being the party city of the southern hemisphere. And I bet you some of Australia's cities would want to counter that. But the Brazilians, I think, do know how to party, and party pretty hardy. But Rio is their Mecca. I mean, that's where they go to party. Okay. Sao Paulo is the biggest city. It's the business capital. They're serious there. But in Rio, they love to party. Well, their meetings were in Rio de Janeiro. So here he was, first time in his life, he was going down to the southern hemisphere, into the going to the party city of the southern hemisphere, so they claim. So he said, I was so excited. And we thought, yeah, we bet you were, He said, yeah, I just couldn't wait. As soon as I got into the hotel room, I rushed to the bathroom to flush the toilet. What? He wanted to see for himself. If you think about it, pull the plug on a sink, flush a toilet, what happens? That water doesn't just go down, it spins as it goes down. You've just created a low pressure area and it spins counterclockwise. He went rushing to the bathroom to flush the toilet and see the water spin clockwise. He had to be a physicist if that's what he was dreaming of doing when he went to the party city of the South. Okay, Southern Hemisphere. That's a dumb story, but he told us that. I did not make it up. That's the Coriolis effect. Okay. The other one that they keep mentioning as if it's a really important thing, and it is, but it's not in our lifetime. It's when they say slow wobble of the earth, they mean slow. All these other things happen in a year, in a day, other things like this. This one, no, this is slow. Slow wobble of the earth's rotation axis. Now, why does this happen? It's a reaction of the earth to the gravitational pull on the equatorial bulge by both our moon, who is our closest neighbor, and our sun, who is the biggest bully on the block. Both of those are pulling on that. Remember, we in our oblate spheroid, we're thicker in the middle than we are at the edges, so it's pulling on that, and that makes us wobble ever so slightly. Now, ever so slightly, 26,000 years for one precession. Hey, we're not going to notice this in our lifetime. In fact, in the whole history of man being able to navigate, so basically our recorded history, since we've become sort of a civilized species, it's been such a short time, our North Star has always been the North Star. However, it wasn't always, and it won't always be. But whether we survive to see it change, that's another story. The way we're going now, I think we're going to self-destruct long before we see much of a precession. But it's changes in direction of the rotational axis on the celestial sphere. And here's what this means. If you've ever played with a top, now I don't know if any of you even remember what a top is. This device, you wrap the string around it, and I think you held it with the point up, and you threw it and yanked the string back, and you made it start spinning, and then for a while, if you got a real good spin, it would stand straight up and just spin, 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 spin. But as it slowed, then it slowly started to wobble a little bit. It's still spinning like crazy, but that's called precession. That slow wobble of the axis, even though spin is really, really fast, the axis is wobbling really, really slowly. That's precession. Okay? Now, that doesn't last very long on a top. It crashes. But right now, the North Star is our pole star. Directly over the North Pole, it's not moving. It sits right there. But do you remember that real bright star that wasn't too far from it on the sky map? Vega? Wasn't very far from the North Pole. At some time or another, in about maybe 13,000 years or so, okay, well, AD 14,000, Vega will be our North Star. I'm not going to be around then, okay? Not here anyway, okay? 14,000, we're in 2,000 right now. Nope, 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 nope. I'm not even sure mankind will be here that long, but whatever. We're on our way very slowly, precessing in this direction, very slowly. Well, actually, we're precessing that way, but it makes it look like our pole star is moving this way. And at some point, 14,000 AD, Vega will be our North Star. Okay, so Polaris was not always the North Star, nor will it always be. And the position of the equinoxes on the zodiac will also change, because if the North Star is moving, if our axis is precessing, that means our equatorial, our celestial equator is also precessing, and therefore the stars aren't moving. Okay, they're staying where they are. So some of those zodiacal constellations won't be on the ecliptic anymore. Others will be there, and they have noticed this for some of them. Right now, I remember one of them. I don't remember which one that was not quite smack on the ecliptic to begin with. It was just so it's now a little further away, and really the constellation right next to it, right below it or above it, I don't remember which one it is, actually is on the zodiac now. But all the astrologers have always named Libra or whatever the one is, and so they're not going to change the name. Okay, even though it's not on the ecliptic anymore. So that's precession. Once every 26,000 years as opposed to once every year or 24 hours in a day. No, this is really, really, really slow. All right. Now we move to 16.3, place and time. Now we've already sort of talked about some of this, but we're going to hit it again. Our Earth's periodic motions provide a basis for determining place and time. Okay. The rotation, because the Earth is rotating, we have to be rotating about something, that axis. That's the important deal. The axis that's run from South Pole to North Pole, that's the important deal. Everything's measured from that axis. One of the main things measured from it, equidistance from north and south of those poles, the ends of the axis, that's the equator. Equator, equal distance from the two poles. So that is the main line on our globe, though it's an imaginary line, that helps us determine place. At least one of them anyway. The easiest to identify. So the rotation provides the axis of rotation useful in determining locations on the globe. Now, the combination of rotation and revolution, we're spinning all the time we're going around the sun, that determines the cycles by which you can measure time. One rotation of the Earth is 1 day. One revolution of the Earth is 1 year. Okay? Now, 1/4 of a revolution of the Earth, that's 1 season. Fall, spring, autumn, or fall, winter, spring, or summer, or autumn, winter, spring, summer. That's a season. Okay? And from that, and I don't know why they chose especially 12, maybe it's those zodiacal constellations, I don't know, but that determined months. Well, actually better than that, the moon determines the months. Okay? M-O-N, M-O-O-N, moon, month. They're related. Okay. So let's start with place. Now, if this were indeed a flat Earth, which many people thought it was for years and years and years, then it's pretty easy to locate where you are. You're so far from the top of a page, or so far from the center of the page, or the right-hand edge, or wherever, you can locate exactly where you are. You're a distance here and a distance there. Okay? But that's hard to do on a sphere. On a curved surface, you don't have parallel lines. Okay? I mean, you sort of do, but they're curved. They're not lines. They're curves. Okay? So we need some other way of doing it. So here's what they've come up with. Now, we're going to do a lab today, and then we're going to do a lab probably next Tuesday, and then we'll do another lab after that, and then about 3 or 4 labs from now, we run out of new stuff to do, and we'll go back and do one on identifying place, latitude and longitude. But we got several labs to do before we'll get there. And what we'll be talking about then has a little bit to do with this, but this is more directly. Okay, so here's what we've got. You got the Earth there with an axis. Now, they're not showing the tilt of the axis. They're picturing it as if it was straight up, just for these purposes. Now, let's imagine that you cut a slice through the Earth, say right here from 90 degrees, right down here through to the equator, and then came over here and cut another slice here. So you took out a quarter of the northern hemisphere here. Okay? In fact, maybe take out the whole half of it, and then put a protractor up against the other half. Now, you can't really do this at too high. I mean, lots of reasons you can't. But if you can imagine doing that, so that the protractor base is at 0 degrees on this side and on the other side. And then you measure up from that, from the center of the protractor is at the center of the Earth, and you measure up from there 20 degrees, 40 degrees, 60 degrees, 80 degrees, and directly up would be 90 degrees. That's the North Pole. Do the same thing in the southern hemisphere. 20 degrees, 40, 60, 80, 90 degrees south. Now, these are circles that cut through the Earth parallel to the circle of our equator. Okay? Now, these are all smaller circles as you go up because there's less and less Earth there to cut. But they're all parallel planes to one another. These define our latitude. Now, these are called parallels because they sort of act like they're parallel to each other. And they're also called latitude lines. This is 20 degrees north, 40 degrees north, 60 degrees north, 80 degrees north, and of course, the North Pole is 90 degrees north of the equator. Exactly same distance from any point on the equator, 90 degrees up. Okay, sorry. I had to cram down lunch. In less than half an hour. And I'm running out of blood sugar, I think. Okay, and I just ran out of Coke too, which is not a good sign. All right, so these are your parallels. This is how many degrees you are north of the equator. Where do we live? 33 degrees, 26 minutes, and 45 seconds. That's not us, everybody. That was where Bessemer was, because that's where I used to teach this course. So that's what we'll base everything is, what it was in Bessemer. Okay. If you're somewhere north of Bessemer, it may be 33 degrees, 24 minutes or something like that. It's not going to be a lot of difference. Okay. So that's how we determine latitude. Again, we'll be doing this in a lab, several labs from now. Okay. And this is what I was talking about. If you were to put a protractor here, at least half a protractor, you would see this is 20 degrees north, that's 40 degrees north, that's 60 degrees north. They don't show 80, they show 90. Now what I don't know is why they didn't use 15 degrees. 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees, and 90 degrees. That would have made a lot more sense, nice and evenly spaced. But they chose 20s. Doesn't matter. Okay. Now, that's how we identify part of where we are, how far we are north or south of the equator. And it can only go up to 90 degrees north and only down to 90 degrees south. Now, in some renditions of this, they'll actually refer, this is how I'm used to doing it, 40 degrees north, N for north. If it was down here, 40 degrees south, 40 degrees, capital S for south. That's how I'm used to doing it. But in some notations and stuff these days, they'll call this just 40 degrees. Down here they'd say minus 40 degrees. Now, I don't really care for that. It makes it seem like the southern hemisphere is inferior to the northern. It's not. Okay, so I wish they'd just stay with north and south. That's what we're dealing with. Now, the other thing that we need, just like you needed how far you were from the top of the page and the center of the book, you needed two coordinates there to determine where you are on a page, a flat sheet, flat earth. You need 2 points to determine where you are on the surface of the earth. One is how far north or south you are of the equator. The other one is how far east or west you are from somewhere. Okay, we don't have an equator going north and south. Okay, we just don't. Everything's sort of equal there. See, the equator is the only what they call great circle that goes all the way around. Maximum circle goes through the center of the earth. All those other parallels go through the axis, but they don't go through the center. The equator goes through the center and the axis is at the center. Okay, so, but all these others, all of them are great circles. So who do you favor? Well, back when they were determining this, Britain was queen of the oceans. Remember, under Queen Elizabeth, they defeated the Spanish Armada, who had been one of the biggest navies in the world. Britain took over and kept it for, I think, centuries. They were queen of the oceans. Okay? And as queen of the oceans, one of the most important places in Britain would have been the Royal Naval Observatory. And that happened to be in a little town east of London, not in London, but east of London, named Greenwich. And the prime meridian, they decided, I guess the British decided this, would be the meridian that went through Greenwich, England, right there where the Naval Observatory was. And that got known to be the prime. Now, prime usually means first, premier, first meridian. But it's actually the zero meridian, okay? That's 0 degrees east or west of the prime meridian. You're right on the prime meridian. So anywhere east of that, and this would be mostly Europe, a lot of Africa, and on around till you got to Asia and India and Australia and all like that. Keep going around. You go around till you get 180 degrees. So it's so many degrees. 90 degrees east, 120 degrees east, 45 degrees east, wherever, how many degrees east you are of the prime meridian. Okay? That's your longitude. Of course, going the other way, you go 180 degrees west. So that, I don't know what these are measured in, 15 degrees west, 30 degrees west. We happen to be along about the upper 80s, lower 90s. I think we're the upper 80s degrees west of the prime meridian. The Atlantic Ocean is over here. You have to cross the Atlantic to get to the U.S., and we're a little further around, somewhere pretty close to 90 degrees west. Not exact, upper 80s, that's where we are. Okay? So North America, South America, a lot of the Pacific would be in the Western Hemisphere. The Eastern Hemisphere is from England all around here. Now there's somebody else come in. I didn't see a name. Let me see. It's not showing me. I'm hitting the wrong button, that's why. No, I don't see anybody else waiting. Okay. Whew, goodness, I need something to drink. You are my fourth class of the day, so I'm running out of steam, especially on a Thursday. Okay, so now we have two things: how far north or south you are of the equator, and secondly, how far east or west you are of the prime meridian that goes through Greenwich, England. Okay, now this won't advance. And by the way, most of the rest of England is west. A little bit that's east of London is east. Scotland would be some of both, but Ireland would be totally west. Wales would be west. You know, a lot of those areas would be west. Iceland would be west. Greenland would be west. And certainly the Americas. I can't get it to advance. There we go. All right. Now, so how do we determine the position on Earth? It's the intersection of the parallels, latitude lines, and the meridians, the longitude lines. And that is defined with respect to the rotation axis. So the parallels measure your latitude, the meridians measure your longitude. So how far north or south you are of the equator, that's where your parallel is, that's your latitude lines. How far east or west of the prime meridian, this is all the meridians are east or west of that, and that determines your longitude. All right, here again, the same picture we saw before, but smaller, 0 to 90 north. Here we see 0 to 60, 90 north. And then this one we didn't see before, but we saw sort of part of it. From prime meridian, Greenwich, England would be somewhere right around there. And you go east, most of Europe is east of that. A lot of Africa is east of that. Most of Asia is east of that. Everything's lots and lots east. The west is the Atlantic Ocean here. Of course, Ireland is right up here, and Iceland and Greenland and stuff. But the Americas are over here in western longitude. Then you got most or a whole bit of the Pacific is over there. Okay. Now, this shows this is the one we saw before. This is going east to 180, and then you go west to 180. Same thing we saw, only smaller. So I don't know why they repeat it. Now, in identifying place, there are a few special parallels that are climate related. And we'll talk about this again in chapter 23 when we're talking about weather and climate. So let's see. Okay. I've named a few of them. Let me name the rest of them. Okay, we certainly know the equator is a parallel. That's 0 degrees, either north or south, it's 0 degrees. That's the equator. You're not north or south of the equator, you're on the equator, 0 degrees. And then this Tropic of Cancer, which is 23.5 degrees north of the equator, that's where the sun is directly overhead during the summer solstice in the northern hemisphere. That is the Tropic of Cancer. The Tropic of Capricorn would be where you are 23.5 degrees south of the equator, and that in the wintertime is where our wintertime, the southern hemisphere summertime, that's where the sun would be directly overhead on its summer solstice, our winter solstice. So these are called the tropics, anything in between the two tropics. Tropic of Capricorn to the south, Tropic of Cancer to the north, 23.5 degrees south, 23.5 degrees north. Those are some special parallels. Climate related, whoa, here comes Jackson. He must have been out and had to come back. Because I think I already had him here today. I'm pretty sure of it. Yeah. Okay. Now, let's go further north. Remember I said that there is a certain portion of the way north. Did someone come in? I think someone probably went out. No, I don't think anyone came in. That in the summertime, the sun never sets, and in the wintertime, it never rises. And this is 23.5 degrees from 90 degrees. Now I'm going to do something now that we'll be doing more of during lab. So let me show you how this works. This is a real simple example. Let's take the North Pole is at 90 degrees. Oh, this isn't writing on this. Oh, there it goes. 90 degrees north. Okay, remember? Now, I don't want to call it 90 degrees. I want to call it 89 degrees and 60 minutes, because 60 minutes makes 1 degree. 1 degree plus 89 is 90 degrees. Now I'm going to subtract from that 23 degrees 30 minutes. That's 23.5 degrees. That's your tilt of the earth. When you subtract those, you get 30 degrees here, 30 minutes here. Subtract these and you get 66 degrees. So anything north of 66.5 degrees north, 66 degrees 30 minutes, is what we call that point where it's 66.5 degrees north. I wish I could, oh, there it is. That is your Arctic Circle. Okay, anything above that we say is in the Arctic. Similarly, when you're tilted, wait, I think someone did come back in that time. Sometimes this thing pops up and sometimes it doesn't. No, I don't see anyone. Okay. Whew, goodness, I'm running out of gas. Okay. So this is the, if this is north, now I think I must be doing that because I don't think anyone's changing here. Okay. They may be coming back, so that's why I try to keep an eye on them. If this is 66 degrees, I can't find it. Oh, there it is. If that's 66 degrees 30 minutes north, that's the Arctic Circle. If that's south, that's the Antarctic Circle. What is that? In what we call our summer season, that's their winter season, so they have 24 hours of darkness anywhere in there. And this, I don't think I did that, but let me see. No, this sort of becomes a pain in the neck here. Okay, but in the what our winter is, their summer, they have 24 hours of daylight everywhere south of the Antarctic Circle. Antarctic Circle would be 66 degrees 30 minutes south. So those are our special parallels. The Earth, Tropic of Cancer, Tropic of Capricorn, Arctic Circle, Antarctic Circle. And those are climate related. In here are super frigid cold, and we call that the Arctic regions. That's the Arctic region, even though it's Antarctic. Okay, these are the tropics. Everywhere between these two are tropics, pretty much. And these regions in here then would be the temperate regions, and that's pretty much where we live. Okay, we do live there, smack in the middle there. Okay, now was that somebody coming or was that me? I don't think it was anyone coming. Sorry, I keep doing that. So those are the special parallels that are climate related. And by the way, that got us to somewhere around page 415. They didn't have this, oh yes they did. Figure 1618 is the figure that you see here on the text, on the slideshow here. Now, so that's how we identify place. I think we're ready to move to, if I can get it to move, to identifying time, measuring time. Now, you probably are aware of this, but I'm not sure you have ever thought about why. Time standards depend on measuring intervals between evenly spaced periodic events. Now here are the astronomical examples. The rotation of the Earth on its axis and the revolution of the Earth around the sun. We've hit that several times now. The spinning of the Earth around its axis, rotation of the Earth on its axis, that's the basis for a day. The basics for a month, we're not there yet, but we're going to get there. That's pretty close to one time of the moon around the Earth. Okay? Pretty close. The season, we talked about those. That's between the solstices. Yeah, we're losing people now, it looks like. Hopefully they'll be coming back because we do have a lab coming up. Okay? I wouldn't want to miss a lab because they're really hard to make up on your own. Now that I'm recording everything, they will be easier, but still easier to do it in person when you can ask questions. Okay? So the seasons are defined as the times between an equinox, a solstice and an equinox and a solstice, a solstice, an equinox and a solstice. Those are your seasons. The year, one time around the sun. That's a year. Now, believe it or not, there are different ways to measure a day, a month, or a year. Okay? Now, excuse me, their terminology here leaves a little bit to be desired. Okay? When you're measuring something compared to the stars are up there, basically they don't move. We spin, that makes it look like they move, but they are fixed in place. Okay? So you call that a sidereal. Sidereal day, a sidereal month, or a sidereal year, or something similar to that. However, when you take into account other issues, like the fact that it's not just our spinning on our axis, we're also moving around the sun when we spin on our axis, that makes your day relative to the sun different from a day relative to the stars. Sidereal day is relative to the stars, and we'll talk about a solar day is relative to the sun. Same thing with months. You have sidereal month, or I just had it on the tip of my tongue and now I've lost it. They have a different name for it. See, they don't use the same names. Sidereal means stars. Synodic month was the month relative to not the stars. Well, we'll talk about it. Year, again, relative to the sun or relative to the stars. Sidereal year, and then I don't even remember the other one. Okay, I can't get this to advance. Let me see if I can make it go. There we go. So let's look at daily time. This is page 415, right-hand columns. Daily time measured because of the relative Earth-Sun motion. Okay? Actually, spin of the Earth and what the sun seems to be doing. So viewed from above the North Pole, the Earth revolves counterclockwise around the sun, but also rotates counterclockwise. Now, here on the Earth, that makes it look like the sun comes up in the east and goes down in the west. In reality, it's sitting pretty steady, and we're just spinning, making it appear, to come up and go down. Now, here's the issue. Okay, someone I think just came back. Oh yeah, there it is, Andrew. No, actually this may be Andrew's first time here today. I believe it is, isn't it? All right, Andrew's here. Good to have you. Now, one spin around our axis is a sidereal day. Relative to the stars are always out there. One time around, it'll be in the same place. Okay? However, we're closer to the sun than we are to any of those stars. So when we're rotating around our axis and the sun's over here, at noon one day, the sun is here. Okay, sun stays there, by the way. We rotate on our axis, but we move just slightly around our uh, around the sun. So when we spin just one time around, you see if we started here, and this is where the sun was noon at this time, and then because we're not just spinning, we're also revolving around the sun. When we get up here, one spin later from here, if you're looking down on us, one spin later from here, here we'd be facing here. Well, that's not noon. Noon is when we're here. So you have to add a few more minutes of spin to get the sun crossing your meridian there. See, the sun crosses your local meridian here, and because we spun, it's a little bit longer before the sun crosses our meridian there. That's a solar day. A little bit longer, excuse me, than a sidereal day. Okay. For some reason, this won't advance until I click the slide again. Okay. It's 3:02. We've been at it for what, an hour and 45 minutes? Is that right? It would have been, yeah, 2:15 would have been an hour. Yeah, another 45 minutes. Is it okay to take a short 5-minute break now? I know we're going to probably break it at lab time, but I really need to get up and move around, son, and I need something else to drink. So you okay for a quick break? Say, let's keep it less than 5 minutes. Okay with that? Okay. Let's do a quick break. I'm going to pause the recording. Remind me to get it started again. The phone rang, and then I was afraid it was my wife doing, something had come up there, and it was a courtesy call from somewhere. I said, look, no, I'm in class now. So everything slowed me down coming back. Okay, so Kendra just came back. I'm pretty sure I already had her marked here. Yes. All right. Now, hope everybody else is back too. This is what we're, yes.
Okay, I want to let you know because I went out and I didn't know why you wasn't letting me back in the class. I didn't know you all went to break. But the lights are flickering on and off, which means I'm losing internet. So I don't know how long I'm going to survive.
Right, I understand.
My problem. That's how I get out. I didn't know it was breaking.
Yeah, it seems like, as I was talking before, we've had so much rain this summer. It seems like it's raining almost every day now, so we're having storms just periodically, and we had a hurricane somewhere in the area, so I'm not surprised that maybe it is. But hang with us if you can. I'll be here unless I lose power until 5:45. So if you do lose us, try to come back. Okay? And sorry y'all didn't get to hear, but I just had to get up and stretch some. I've been, like I said, talking since 8:30 this morning, and actually started earlier than that because my boss called and we had to work out some problems. And so anyway, I just had to get up and move around some, and then everything else happened. All right, so sorry you had to wait. Here we are. Now, what we were just talking about before, for some reason I have to click on the slide before it'll move. Here's what we talked about. The daily time is different with reference to the sun than it is from the stars. And this is what it's talking about. What we call noon is the time. Now remember, we talked about if you're facing due north, and frankly I'm sitting here almost facing due north right now, or where I'm sitting. Okay, so if you were to draw a line from due north directly overhead to due south, that is called my local meridian. Okay, that's the meridian that I happen to be sitting on right here. Y'all are at maybe a slightly different meridian. Unless you're directly north of me or directly south of me, you would have a slightly different meridian. Now, technically what noon is the time when the sun crosses that meridian. Okay, now everybody would have a different noon. Okay, and that's called apparent local noon, because right where you are on this longitude, where I am right now, when the sun crossed that meridian, and by the way, that was the highest point the sun will ever be all day. It started down there when it rose this morning. It'll set over there. That's the highest point it will be all day long. Okay, right there when it crosses my meridian. That's my local apparent noon. That's how we used to call it in the Navy. They call it here apparent local noon at my particular longitude. Okay, now that's where we would start the clock for one day. Apparent local solar time based on the sun would be the given position, given by the position of the sun in the sky exactly the next time it crosses my local meridian. It can be measured by what they call a gnomon, really strange word there, also known as a sundial. You have a picture of that, I think, in your book. Yeah, on page 416 you'll see a picture of a sundial. We have a little fake one out in our yard, you know, at the edge of a sort of a plant garden area. Okay, now this is not the time shown on clocks, because everywhere you were on a different meridian it's going to be a slightly different time. So we just have to take an average. So what we call mean, that doesn't mean it's ugly or nasty or anything, that means average. The average solar time is the time average from one apparent noon to the next apparent noon. Okay, now it's averaged over two effects. Okay, first, remember, we change our orbital speed. Why? Because sometimes when we're further from the sun, which we happen to be, we're sort of far from the sun now, but we're coming closer. So actually the Earth's speed is speeding up just a little bit, not a lot, but just a little bit. So that's changing. And then the second thing is the equator is inclined to the ecliptic, so that makes a little bit different of an angle every day. So what is mean solar day? Average solar day, that's just right at 24 hours. That's the average time from one noon to the next noon. Now it won't be every day that way. Some days will be a little bit longer, some days a little bit shorter, so that's why we average them. Now, that's a mean solar day. Solar day because it's when the sun crosses our local meridian. Okay, now, here's the other kind of day. The length of time required for the Earth to rotate once on its axis. Now, that would probably be your first guess of what a solar day is. I mean, a day is. But that's a sidereal day, because a sidereal means relative to the stars. Now, if you were, in the middle of the night, to be facing due north, and just at some time, say this really bright star or something happens across your meridian, say, hey, I'll remember that from the next night. So the next night when it crosses, guess what? That would have been the situation right here. That star would have crossed us right here, and the next time would have been right here. But that's not a solar day, because the Earth had to spin just a little bit further to pick up the next noon here, but that would have been one day sidereal day based on the stars. So, whoops, one more slide. The interval between two consecutive crossings of the celestial meridian by a particular star. The little variation is because the Earth's constant rotational rate, okay, but more so because we have a revolutionary rate. I think that's what they meant there, but they said rotational. So let's go back. An apparent solar day, the interval between two consecutive crossings of the celestial meridian by our sun, not by the star. So sidereal day, two consecutive crossings of a celestial meridian by a particular star. Okay. Now, the revolution about the sun changes the Earth-Sun orientation about 4 minutes a day, about 4 minutes longer a solar day, because we have to spin just a little bit further, just like this showed here. We have to spin just a little bit further before we get the sun over our meridian again. That would be about 4 minutes longer. Now that was an exaggeration there, but that's what it is. So they have this on the wrong side. This here, 23 hours, 56 minutes, and 4 seconds, that's the sidereal day. That should be over here. The one we had back here, 24 hours, that's a mean solar day. That should be right here. And you see the difference is just right at 4 minutes. Not exact, but close. 56 seconds off from 4 minutes. No, 4 seconds off from 4 minutes. Okay, so that's different days. We use solar days. Okay. Now, if you think about it too, as we make our way around the sun in 365 1/4 days, if you think about it, that made us spend one more time, because here we were looking at the sun from this side, and then we're here and here and here and here and here. We've also spun one more time in that day. 4 minutes a day over 365 days a year, that's going to come up really close to one more day. So that's the other reason. Now our equation of time. This is an interesting concept, and it's sort of hard to figure with, and this is what we're going to be doing today's lab on. Okay, even though today's lab was based on the last chapter, we're going to be doing it today. So if we can get this covered today, this will make the lab make more sense. Okay, this traces the yearly variations between apparent local time and mean solar time. Okay, now here's what you would do if you had the ability to do it. Unfortunately, I'm facing due north now. The sun is actually back there. It's always above the southern horizon, not above my horizon now. So I should have been turning around when I was talking about, thing, but I was facing the camera. Okay. Now, if I was back in the southern facing bedroom, one of those two windows, and I just happened to have that window covered with black plastic, so it was perfectly dark, every window in the room covered with dark plastic, and just had a little hole due south. Okay, and that little hole allowed the sun right at noon, when it's the maximum point above the southern horizon back there, maximum thing, at that time, right at that local apparent noon every day, I marked on the floor where that sunspot was, where the sun shone right through that hole and where it was on the floor. I'd have to move furniture and that kind of stuff. My wife wouldn't like that, especially if it's going to last a whole year. I did that every day of the year. It wouldn't be in the same spot. Sometimes it would be in the summertime, it would be closer to the wall because the sun's higher in the sky. In wintertime, it would be further because the sun's lower in the sky. But not just that, it varies right to left as well. Why is that? Because sometimes the Earth is moving more slowly, sometimes it's moving more fast, sometimes it's tilted differently. That would make a figure 8 on the floor. If I did it year after year, it would just trace right over itself every time. Okay? That is what we call the equation of time. As it says here, two effects. Oops, here comes Andrew again. I already had him here. Thank goodness he's coming back. Okay? Now, let me see if somebody else came in. I don't think they did, but let me just check. I know it's been happening. Other people have been telling me the same thing. Okay? Okay. I think storms are in the area, and certainly storms are between us and the West Coast where Zoom is. Is it? Okay. Yeah, it's Karen's brother lives in Louisiana, and the parish next to theirs, about 91% of their residents are without power today because of the hurricane that came through. Laura, I think it was. So anyway, things are happening. Two effects that causes figure eight. One, because of the axis tilt. That's why you have the difference distance one way. The other is our orbital speed. Sometimes we're going faster, sometimes we're going slower. That's what gets us off this way. So we have a figure eight this way and that way. So you get this figure eight on the floor. Now this equation of time is the cumulative plot over an entire year. And this, I think, is what it looks like. I can't get it to advance. No, this is a weird thing to put here. This just shows the sun's path. This is as an equinox when the sun's directly over the equator. That's an equinox. Let's call it the spring equinox. When it's as far north as it can go, which is the Tropic of Capricorn, and you see it right there, just under 30 degrees, 23.5 degrees north, that's where the sun is on summer solstice. And you see it's not far from being directly overhead for us, but it's never. And then it starts going down again, and here's your autumnal equinox when it crosses the equator again, and then the winter solstice is when it's down here. Of course, if you live down here, you call that the summer solstice, okay? But that's when it crosses just touches the Tropic of Capricorn. That's the 23.5 degrees south. And then it moves on like this. And that's one reason for part of the equation of time having that figure eight. That's why it goes back and forth this way, okay? Because of the tilt of the earth. Okay. This one actually shows the minutes away from pure noon, you might say, and in early January you're 5 minutes beyond that, and then so like someone may have either come in or left. Nope, don't have anyone coming in. So hold on, coming back. Here you get the maximum up here, and that's about 15 minutes or so, and that looks like to be mid-February. And then you're right on the money here in early April. You're off a bit, a local minimum, about -5 or 6 here around early May. Back right on the money around mid-June. Maximum this way, off plus maybe 4 or 5, and that would be in mid-July, and then back right on the money then in about this time of year, okay, just past early August, okay, and then farther aside, behind clock noon, that would be early October, late September, early October, which is coming up, and then right back on the money in late November, early December, and then you meet right back where we were here. Now, if you were to take this and fold it right there in the center, fold it into each other, that forms your figure eight. Here's a small part of the figure eight here. Here's the big part of the figure eight here. If you folded those together, that would give you your equation of time. Okay, let's see if they actually show it. Can't get it to advance. No, they don't. Okay, now I'm going to find it for you. I'm going to try. Oh, there it is. Okay. Now this is sideways. Okay, there's that figure eight. Okay, it's to me a little too thin or a little too long, one way or the other. Most of the time it shows up a little fatter than that, but that's approximate. In our lab, we will look at one that is more exact than that. Okay, that's the lab we'll be doing today. All right, now we got about 30 minutes or so, no, 15 minutes before we'll start that lab, 16 minutes. So let's think about time zones. Here we're again looking at time. If you think about, the Earth has 360 degrees all the way around the Earth, right? There are 24 hours a day, right? Now, when the sun is rising here over Birmingham, Alabama, it's setting somewhere on the other side of the world, maybe in China somewhere. Because we're facing the sun, or the sun's just coming up, it's just going down there, okay? Because we're a globe. Half of us are facing the sun, half of us are not. When it's noon here, it's midnight over on the opposite side. So 360 degrees are divided into 24 hours. Well, if you divide 360 by 24, pull out your handy dandy calculator, your telephone, whatever you use there, okay? And you divide 360 divided by 24 equals exactly 15. 15 degrees for every hour. So there are 24 time zones, each one of them right at 15 degrees wide. Okay? Now, these are adjusted for local consistency. Now, what does that mean? Here's what it means. Let me show you the graph. Yeah. Here it is in the US. Now, the time zone should cut Maine in two, and this little bit of Maine here should be on Atlantic time. But we don't want that little bit of Maine to be off what the rest of us are, so we adjust this for local consistency. Even this part of Maine here is counted Eastern time zone. Okay, somewhere here, from here or coming down here, somewhere here is where Central time zone should begin. Well, you see the Alabama-Georgia line's not far off, but part of Florida, sure enough, is in Central time. Part of it is in Eastern time. Most of it is in Eastern time. The Georgia-Alabama border, even though it's not right along that meridian, we make that the border. So up here they should be Central time, but Georgia should be Central time too. Down here, this part of Alabama should be Eastern, but we make it Central just to keep the whole state on the same time zone. Except for, are any of you from somewhere over there near Phoenix City, Alabama? Do you know where I'm talking about? You know where huh? No. Phoenix City, Alabama is real close to Columbus, Georgia. Columbus, Georgia has a huge, one of the biggest army bases in the country, Fort Benning. A lot of people from Phoenix City don't work in Alabama. They cross the border to Georgia and work over there. And because of that, it seems like I've heard that Phoenix City stays on Eastern time. They don't go on Central time, just because so much of their economy and everything else is based more on Columbus than it is anything in Alabama. Okay, now I don't know that that's true, but I've heard it. Poor old Tennessee is such a long state. Chattanooga, I think, is in Eastern time zone, but Nashville and Memphis are in Central time zone. Kentucky, the same deal. They had to make a decision here. I think Richmond is Eastern time zone, but this part of Kentucky is in the Central time zone. Indiana, same thing. Most of Indiana is in Eastern time zone, but this part down here, it's closer to these regions down here, which are can't think what the big town is, but they associate more with Central time zone. I know what happens up here. Chicago, Illinois is right there. So this part of Indiana stays on Chicago time, not on the rest of Indiana time, because most of the people probably commute and stuff and go there, so they go on Central time. Michigan, just to keep the Upper Peninsula on the same time with the rest of the state, they zip it over there. Wisconsin, part of it probably should have been on Eastern, but they kept all that on Central. Okay, Minnesota, this little tip probably should have been on Eastern, but they wanted to keep the whole state on Central. Okay, now, why in the world this happens, I don't know. Okay, North Dakota looks like they went, and South Dakota too, went way out of their way to mess up the time zone here, but I don't know the reason for it. Okay, here in New Mexico wanted to stay all on the same time zone. I don't know why this is so, but this is Mountain Time. This is Central Time. I know what's happening down here. This is the very western tip of Texas. Really should be Mountain, and they are. The main reason, Santa Fe, New Mexico is the closest big city. They wanted to be on the same time as that. They did. Dallas and Fort Worth and Austin, all of them are way over here. They're far more related here. Same thing out here in Nebraska. People in western Nebraska head down to Denver. They don't go back here. They go to Denver, so they got on Mountain Time. So that's the reason here. That may be the reason for this division here. I can't say for sure. Idaho, this part probably relates more to Washington than it does to Montana, so they got on Pacific time zone. This part wants to stay, in fact, part of Oregon wanted to stay with Idaho. Probably some of the bigger cities in Idaho are in here. So it's just adjusted for local consistency. Whatever works for the community you're in. That's what this one meant. Now, they have this blurb on daylight saving time. The clock set ahead in the spring, spring ahead, fall back for an extra hour of sunlight during the summer evening. So that's mostly because summertime we have close to 14 hours of daylight and only about 10 hours of darkness. So you don't gain anything except it makes the sun come up. You set your clock so you're earlier in the morning. Here's my theory, and no one will claim this, but I think it's because the bankers like to play golf in the evening. It gives them an extra hour of golfing, or the executives. It doesn't bother us. I've heard it blamed on agriculture. It has nothing to do with agriculture in my mind. The cows, if they need to be milked, it's the same time of day, whether you're daylight saving time or thing. It's not by a clock, it's when they need to be milked. So it's not got anything to do with the agriculture. They claim it does. Now, the weird thing about this, I wish we had a globe here. I would show you on a globe. If the prime meridian is over here in England, on the opposite side of the prime meridian, where you're 180 degrees from that, guess what? It's morning on one side, okay? It's one day on one side, the other day on the previous side. What? Well, because if this is midnight, early morning hours on a Wednesday, you go around and it may be noon on that Wednesday here in London, and then you keep on coming around. It's about 6 o'clock in the evening that same day here. No, not at the same time. When the earth is spinning, this is what's happening. It's morning here, say on a Friday morning. They're already in the Friday morning over there. And then soon it'll be Friday morning in London, and then it'll be Friday morning here and stuff. And then by the time it gets Friday evening here, it's Saturday morning on there. So here, this is called the International Dateline, the 180 degree meridian. On one side of that, it's one day. On the other side, it's the other day. Okay? It's designated to correlate days in 24-hour time zones, so it's midnight one day on one side and another day on the other side. It's bizarre. Now here's a dumb naval story, whether it's actually true or not, and that, by the way, happens in the middle of the Pacific. I'll show you the picture of that right here. There's the international date line right there. And again, adjusted for local convenience, local consistency. Okay? Supposedly, there's an island somewhere in the Pacific that sits right on the international date line. I'm sure there maybe is more than one. And supposedly that island in the middle of the Pacific there that's sitting right on the international date line, somebody bought him land that straddles the international date line. And on that land, he built him a bar that went across like this, so that half the bar was on this side and half on that side. So when it became Sunday morning on this side and he had to close, it was still Saturday night on this side, so he stayed open. And then when it became reverse of that, he opened this side and closed that side. I don't know if that's true or not, but they claim somebody had done that. Now, why the local consistency here? Well, Siberia actually crosses over. Here comes Christian back in, and I'm sure I've already got him marked here. Yep. Okay. I'll bet you that was him just coming in. Let me just make sure nobody else was waiting. No, got them all. Okay. Now, to keep Siberia on the same day as the rest of the Russia, we jugged it over here. But then the Aleutian Islands that go here, they belong to Alaska. And we wanted to keep them on the same day as Alaska, so we jut back out here and get them all on the same day. Down here, there's certain of these island nations. I think it's called Micronesia somewhere in here, but also New Zealand is awfully close to this, but some of the islands out here that belong to New Zealand, they wanted to keep on the same day, so they jutted out here. So again, even the international date line has the jut there. Now, when I was in the Navy for the first 3 years anyway, we were in the Pacific all the time. And every time we crossed one way, we picked up a day, and when we crossed the other way, we lost a day. And it was just amazing to me. We always lost the Saturdays when we crossed one way, and we always picked up in the middle of the week when we went the other way. So we had 6 work days one way and kept the 5 and only had 1 weekend day the next way. Let me make sure nobody else is coming in. I don't see anybody. Okay, but that's international date line. Probably beat that into the ground. Okay. Goodness, it keeps popping up here. Okay, I think we're all right. Must be storms in the area and people are getting bumped off and bumped back on. Let's see if I can advance. I don't think I can without touching. Okay, here we go. Now the question is, in 3 minutes, do we have time to talk about yearly time? Maybe not, so let me just hit on one of these examples here. If you're on page 420, example 16.5, how many time zones is Honolulu, Hawaii, which is 21 degrees north, 158 degrees west, behind New York City, which is 41 degrees north, 74 degrees west? Well, guess what? It doesn't matter at all, the northern, okay? That has nothing to do with time zone. That's only the western. So let's see what we had here. Oh, here comes Angelita. She must have got bumped out again by weather. Okay, welcome back. Okay, so let's do that calculation they just did here. Hawaii was 158 degrees west, and New York City was 74 degrees west. Let's subtract that, and what do you get? 84 degrees west. That's the difference in the longitude. Well, every 15 degrees you have a time zone. So let's divide that by 15 degrees. And 84 divided by 15, I've lost my phone here. So 84 divided by 15 would be about 5.6. So I'm guessing that's 6 time zones different. Does anyone know for sure? From Eastern time to whatever that is in Hawaii, is that about 6 hours difference? Anyone have any experience with that? That seems about right, because it seems like it's 2 more hours difference from Pacific time. So let's see what the book says. Yes, they said rounds to 6 time zones. That's what we said. How many time zones ahead of Denver, Colorado is the Bay of Fundy in Nova Scotia? And again, we don't care about the north-south. That doesn't matter. But Denver is at 105 west. If I could find my pen. Where is my pen? There it is. So 105 degrees west. And the Bay of Fundy in Nova Scotia is 66 degrees west. Okay, my dog's going to be upstairs pretty shortly because we are getting the storm right now. So you may lose me. So that's about 39 degrees difference. Divide that by 15. And that's almost 3. So we'll count that 3 time zones, and that's what they say it is. 3 time zone difference. So this was 6 time zones difference. If I could find my, here it is. This is 6 time zones. This is 3 time zones. It's raining pretty steadily here. This is almost like being in Guam. It rained every day, except sometimes it rained twice a day. Okay, we are having the rain this year. And the good news with that is I've had the most pears on my tree I've ever had. Okay. All right, how are we doing? We went a minute over. So we'll begin next time with yearly time. Okay, now this is the place where we stop and we'll start the lab. So I think what I'm going to do is turn off my PowerPoint here. So I'll probably lose screen share right here. That's not what it was supposed to happen. How did that happen? Okay. Okay, this is where we'll be beginning next time. Okay, I'm going to discard the ink things, and let's just move this over here, and we will end that. And we're okay with screen sharing. Stop. All right, now what I'm going to do now, I'm going to need my pad, and we might need my calculator too, but I'm going to move my calculator down there. Okay, I've got thunder and lightning. That's why I thought, oh, I have my door closed. So I bet she's outside the door right now. She doesn't like thunder. Okay. Trying to think the best place to go to this. I think what I'll do is go to my, wait, here we go. Let's go here. You can't see what I'm doing here, but I want to end that anyway. I'm glad I went there. Okay. I know it sounds like I'm talking to myself, but as my dad used to say, well, that must be an intelligent conversation. He was kidding, of course. Okay. Okay. Now, I don't think I'll need the book, so I'm going to set that out of the way here. I think I'll scoot my computer over so I have more room to work. Now, where I'm going now is my computer, and go to my USB and go to Physical Science 111, and let's go to Lab 2. Now I sent this to you a couple days ago, and this is a little crooked. Sorry about that. Do all of you, oh wait, let me pull up Zoom so you can see this too. Okay, did y'all get this lab? Now I've got to move some things around again because now it's on the week 2 activities, not activities. Okay, under week 2, the first is the overview, and the next thing below that is the resources and materials and stuff. And the one that deals the PowerPoints are at the top, and then there's the what do they call it? Recorded lessons. That refers you back to week 1, to the YouTube video link. Then the thing that says handouts, that refers you to week 1. And then somewhere down there, right before the bottom, it says labs. That's where it is.
Well, this is Diana.
Yeah.
All our labs being posted on the Physical Science 111.
Yeah. Let me show you where I'm talking about because it's hard to do. So I don't know if I still got this open or not, but let me see. Yes, I do. Yeah. Okay. There. Oh, okay. Okay. Let me answer both questions, one at a time though. Okay. Now, let me get out of the messages. This is where I was showing you where the messages were. That's the envelope thing for those who weren't here then. That's called Blackboard Messages. Test I put there. Okay. So let me go to Physical Science 111. That was in Physical Science 111, but I shouldn't have gotten it. Okay. Now here we are. Okay, you can't see it. Let me bring up the new share here. Here, under here. All right, can you see my... I'm going to move y'all out of the way. Okay. Now, this is my content page. This is what you see, except you don't see the ones that have slashes through them, hidden from students. Okay? If you come down here to weekly assignment and activities, okay, you have to open this over here at the down arrow when you open it. All right. Now I'm going to go through this again. Week 1, generally it's over with. I can't get it to open though. I don't know why. Okay, let me try opening it here. There, it finally opened. The overview and weekly to-do list, you can go back and see it, but that's not important now. This instructional materials, lessons, PowerPoint, videos, handouts, and so forth. If you click on that, and it opens. Okay, here are the PowerPoint slides. This was for last week. We've been doing this one in 13 and 16 this week. Here's the YouTube video, recorded lectures. This is the one that takes you the whole playlist. You can pick out whichever ones you want to look at. Here's your research paper document, your instructions. Here is my locator card, and then those are the pretty pictures from Hubble. Scroll on past those. And there was that other file I sent you, the space objects in perspective. And then here was the lab we did last week. There's the sky map, and there was the lab form that you filled out. Okay? Now, let's leave this and go to week 2. But I just want to remind you what's there. Okay, so let's leave that and close up week 1 and open up week 2. But for some reason, it's not opening. So I'll come over here and open it this way. Okay. Now this overview and weekly to-do list, this is what we're doing this week. I'll just pull it up to show you. It's just blah, blah, blah about what we're doing this week, That's what I think of it too. It's awfully slow. Okay, there's the overview. Here are our objectives, and here were the what to do. We finished chapter 15. We started on 16. Okay, close that. Oh, and by the way, it says complete lab 2. That's what we're doing today. Okay, take test 2. I'll be posting that after lab tonight. Okay, and then start reading on 16. We've been on that already. Okay, so close that one. Now, here's where you were asking about. Instructional materials under week 2. Instructional materials here, click on that. It's so slow. There's the PowerPoint. We're doing 15 earlier in the week. We're doing 16 now. Recorded lectures, go back to week 1. That same link takes you to all those lectures. Handouts, go back to week 1 for the research paper instructions, locator card, and the other links given in week 1. The labs, this is the lab for this week, lab 2. Now I was not going to open it here, but you could. I could go to these 3 dots here. You see this has an icon, but when you put your cursor on it, it doesn't underline. So you have to come here. When you click on the 3 dots, you'll see it says download original file. Now if I were to click that, then it would download down here, and when it finally downloaded, I could click on that and it would come up. That's what it is. Now I've already opened it from another way, so I'm not going to open it twice. Do you see that? Now, your question earlier was what you do when you finish it. Okay, well, I'm going to get out of this. This is where your labs will be. Next week's lab will be under week 3, right here. Next 3 PowerPoints will be at the top there. Okay, the recorded lectures and handouts, they're all referring back to week 1. There's just no reason for me to put them every time there. Okay. Okay, so I'm going to close this out for now. Okay, now I'm going to close week 2 and close weekly assignments, and I should be back here. Content. Now what I can't figure out is why I can't see the envelope here, but I can't. So what I have to do is go out of this and come back into that. I don't know why Blackboard is so obtuse. Now I can see it. Okay, I'm right where I was, but now you can. So where do you send the lab? Some people send it through Blackboard messages. Just like I send you your test through there, some people send the lab through there. If you don't want to use Blackboard messages, send it via email. Okay, now this is a big, long, ugly lab, and I don't know how you want to do it, but whatever is most convenient for you. In fact, some people don't even mess with it. They just write the answers down, but be sure that you number correctly so I'll keep up with what you're doing. Okay. Yes.
Your last lab was in editing mode where I could actually work it from the screen. Are they going to be different? Are they not going to always be edit options?
Yeah, just about every lab is different. The last one I did the lab part. I couldn't do the map part, but you didn't have to write on the map. I did that. That was a PDF, I think. But the other thing was a Word file that you could directly copy on. This one's a PDF because I don't have an electronic copy of it. I had to take pictures of it, and that's why it's sort of crooked. Okay, so here it is. That's because when I was holding the iPad, I wasn't holding it perfectly straight. I'm not very good at this stuff. Okay, all right. So here's today's lab. Can y'all see this? And sure enough, it's in PDF. You can't really type on it. The first part is, pardon me?
Yeah, this is fine. Can we just print it and write on the paper?
Absolutely. If you've got a printer, you can certainly do that. Okay. Not everybody has printers. I've had some students who send it to Office Depot or someone like that, and they print it for them. Or maybe the student worked at Office Depot. For some reason, everything that student sent me came from Office Depot. I don't know why. Maybe she took it there and sent it. However you can get it to me. If you can print it, yeah, print it right on the lab and send it back. Now, I pointed out a couple things for you in a minute, but this said you're required to do the first experiment, which we couldn't do. We could not do the first experiment, so I made up a new one. I will explain anything that you gathered from that you need here. Now, first, let's talk about, we talked about this in class today. When the sun crosses your celestial meridian, when it crosses it every day, technically that's your local apparent noon. That's the fundamental reference for a measurement in time. But it's not the same day to day to day, so they do an average. So the interval from one noon on one day to the next sets the length of a solar day on average. Okay. The subdivisions of the day, and they talk about this. The rest of this is blah, blah, blah. So I'm going to just scroll through the blah, blah, blah. Some of it's really interesting blah, 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 but you'll have to figure out what you want to pay attention to and not. They talked about sundials in the early days. That's how they measured. And again, I didn't hold it very well, but straight, so it's tilted the other way here. Okay, they keep talking about sundials and stuff like this. So here's the procedure. So guess what? Page 1, even though you'll probably print it, if you don't want to send it to me, I don't need page 1. I already know what's on page 1. So let's look at page 2. It's not page 1. Let's see if they have a page number there. Yeah, that was page 369 out of the lab book. I don't need page 369. You can send it to me if you want to. I'll try not even to print it, but if you want it, if it's easier for you to send it, send it. Okay, when you get down on 370, procedure. Okay, now this again is pretty much well worth a read. It's talking about the same thing we did in class, that from one noon to another noon, like we talked about on the previous page, that's a solar day. It's not the same as one spent on the axis, because that's a sidereal day. One day from a star in one position to the same position the next day. That would be a sidereal day. Okay, now first we'll adopt the geocentric approach, blah blah. So I don't need page 370 either. It's just talking about what's happening. So here we're on page 371. Here is the first question. See the number 1 here, wherever my cursor is, right there. Here's the first question. This is the first thing you need to hand in. And again, if you print this off, this is the first page you need to print. So let's do this. Okay, and we sort of did this in class, but let's do it now. Okay, now I don't think I'm going to be able to write on this screen. I'm going to try if I can. No, it will not let me write on this screen. Okay, so here's the deal. The sun moves 360 degrees around the ecliptic. In other words, we move around the sun 360 degrees in 365 days. So it's almost a degree a day, right? 360 degrees in 365 days. Almost a degree a day along the ecliptic. Therefore, the sun is about 1 degree further east of where it was the next day. Now, they're talking about the vernal equinox. That's where they're starting. On the day when the equator and the ecliptic are right on top of each other, that's the day 1. The next day, the sun's moved up the ecliptic 1 degree from where it was that previous day. So it says calculate how long you have to wait for the sun to cross your meridian that day, because it's a little bit longer. So here's what we do. Oh, I can't do it there. I'm going to have to go to a whiteboard. I have 2 pads. The computer pad I move with my finger. The other pad, the Wacom pad, I use the stylus. And I was rubbing my finger on the Wacom screen. So let's go to a new share here, and this will be the whiteboard. Okay. Now I've got to move some things around here too. Sorry about this. Move y'all back over there. Move this taskbar. Y'all can't see what I'm talking about because all you see is whiteboard. But I only have a limited amount of room to work, so I have to get everything out of my way. All right, that's about as good as I can do. All right, so what we have is 1 degree, okay, that's how far we have moved in that time. Okay, now let's think about what our ratios are. 360 degrees, that's how far the Earth spins in one 24-hour period, right? 24 hours. Do that division. 360 divided by 24. We just did that already. That would be 15 degrees in 60 minutes, right? Because this was 24 hours, so this would be how many degrees in 1 hour. 1 hour is 60 minutes, okay? Well, if you do that division, that would give you 15 will go into 60, 1 degree in 15 into 60, 4 minutes. So that's the calculation you need to do to determine how much further we have to go to spin that 1 more degree, about 4 minutes longer. And that's why, if you remember on the slide, the sidereal day was 23 hours and 56 minutes and 4 seconds. The solar day was 24 hours, right at 4 minutes difference. So that's the answer to that's the work you have to show to do. Oh my goodness, I just remembered something. I'm going to have to crash for a moment here. I don't think when I came back from break that I started the recorder again. Did I? Oh my goodness gracious. But I want to get the lab on the recorder. Now I got to get rid of this whiteboard. Okay. Okay, I think I've got to get rid of this. Sorry, I'll come back. Let me go here. Nope. Okay, I think I'm going to have to take everything down. Sorry about this. Let's minimize. Oh, here's what I'll do. I'll just minimize. I might be able to get to it. I can't even see my timer. Oh, the recorder is recording. Good. I hope I didn't stop it. Maybe I did turn it back on. Usually I see, you can't see it, but usually I see it over here, but it's not recording there. I wish I could see the time happening, but I don't see it. So I'm just going to have to trust it's still running. Okay. I sure hope it is. Why can't I see that? See what blowing it up will do. That doesn't help any. Okay. I can't tell. see if it's still recording. Let me see. Okay. Okay, it says it's recording. I hope it is. So I'm going to minimize this and go back. I just don't remember doing it, but maybe I did. Okay. Now I have to find I hope this is it. No, that's not it. Okay, maybe since I minimized it, I've got to open it back again. Here it is. There we go. Now, whew, all right. Now I'm going to move y'all again. This is such a pain. Okay, so that's the calculations you need to show here. And what's the answer? Calculate how long you have to wait till the situation happens in minutes. 4 minutes, right? Now, here is another. Figure 40, this is number 2. Figure 48.3 depicts the sun's apparent motion along the ecliptic where the zodiacal constellations are found in a heliocentric perspective. As the Earth orbits the sun, the line of sight of the sun toward the background stars also moves. For example, blah, blah, blah. This diagram shows the sun in Leo. A month later, it will have moved enough so that Virgo lies behind the sun. Do you see a question here? No. I can't find a question, never have found one. So number 2 is okay to leave blank. Usually, if there's a question number and a blank, you fill it in. There's nothing to fill in, so leave that alone. Okay. Now, this is what we were talking about before in the thing. In late March, when the sun is right on the celestial equator, there's the ecliptic, here's the celestial equator. When they cross, the sun's right there at noon, right there. The next day, the sun has moved ever so slightly because it's going spring to summer, so the sun is getting a little higher above the celestial equator. So it's moved sun. So for our local meridian to cross this, we have to spin just a little bit further. The diagram in your book showed that, and that's what we just calculated. How long it took? 4 minutes for us to go from here to there. Okay? Only about 4 minutes longer. Okay, that was the diagram for that. Oh, and here it is, shown the other way. One spin later, we're right here, but we have to move here to get spin just enough to, so this would be, and this is exaggerated, this would be 23 hours, 56 minutes, and 4 seconds here. Here's another 4 minutes longer, and that's when we get our next local noon. That's what they're trying to show. Of course, their scale's off, but that's okay. That's what we did for question 1. Okay, here was what question 2 was talking about. Okay, the Earth is here, and here we're in Leo, whatever that means. I don't even know what month that is. Is that June or something like that? 1 month later, we're here, and the sun is blocking Virgo now. Whatever month. I'm just going to guess July. But there never was a question. Okay, so I don't know. I don't think I'm right there because Sagittarius is December and this is January, I think. So this would be November, October.
January is an Aquarius and a Pisces. No, Pisces.
I don't think so. I think I'm Capricorn. I'm January 7th.
Oh, okay.
I think. I don't know. I don't follow these things. I don't even know what that is. Okay. Yeah. So anyway, let's move on. That was what question 2 was referring to, but they never asked a question, so I don't know where they were going with it. here is where most of what we're going to do today is. The analemma. This is also called the equation of time. Also, another word for sundial. Analemma. Okay? Analemma. Get that. Important word. We're going to use it over and over and over. This is that figure 8 that we talked about, and here is how it looks. Now, I can't get the whole thing on the screen at once, but let me show you. The horizontal axis is given in time. This is local noon, and this is 2 minutes one way, 2 minutes the other way. Now, let's see if they told anything here. I don't think they did. Whoa, come on back here. Yeah, the daily difference between clock noon and noon by the sundial. Okay. Now, the vertical axis, the horizontal axis is time in minutes. The vertical axis is declination of the sun. Declination of the sun means, okay, here's the ecliptic. I'm sorry, the celestial equator. When the sun is down here, it's so many degrees south of the ecliptic. When it's up here, it's so many degrees north of the ecliptic. Notice that all the months listed here see, there's late March, there's equinox when the sun's directly on the equator. Okay, here's the equator. The sun is right on the equator in late March. That's spring equinox. Everything here is spring. There's April, May, June, July, August, September, until we get September 21st. That's the autumnal equinox. After that, you're in the winter months. The declination of the sun in the winter months for us is south of the equator. Okay? Well, for everybody, it's south of the equator. And here we have late September. I'm not sure I can get it all on here. See, it's not even a very pretty 8. Okay? So here we have late September, October, November. These are the winter months. December, January, February, March. All that time the sun is south of the equator, celestial equator. That's the winter months. Now, the fatness down here is because we are actually closer to the sun then and moving more rapidly, so we cover more ground then. When we're farther from the sun and moving more slowly, everything was compressed at the top half. Okay. Now, the other thing that's measured here is the day of the month. Here is the end of September, 1st of October. September has 30 days, so this is 1st, 2nd, 3rd, 4th, 5th of October. 6th, 7th, 8th, 9th, 10th of October. 11, 12, 13, 14, 15th of October, and on like this. November, 1st, 2nd, 3rd, 5th, 10th, 15th, 20th, November. December, here's the 30th November, then the 1st of December, 2nd, 3rd, 4th, 5th, 10th, 15th, 20th, 31 days in December, so it goes to here, then January 1st, 2nd, 3rd, 4th, 5th, 6, 7, 8, 9, 10, on like this. 28 days in February, there's 25, 26, 27, 28. 1st of March is right here. So this is how you read the days of the year. So you have declination of the sun on the vertical axis, time on the horizontal axis, and then on your analemma, you have the days of the year. We'll use every one of those. Now, this is given in degrees rather than time. So this is degrees that you're off. And remember, 1 degree was about 4 minutes. Let's go up here and see if that matches. 1 degree, well, 1 degree is right here. So here's 0 degrees, 2 degrees. So 1 degree is right here. Follow this line up here. Okay, now I'm going to have to move my cursor, so you keep your eyes on this line right here. You see where I am? Okay, you keep your eyes there because I have to move my cursor over here. Up, there it is, 4 minutes right there. So sure enough, 4 minutes represents 1 degree. So you have a lot of things going on this analemma. Very useful device. Okay, and we're going to use this the rest of the lab. Okay, now, oh no, this one's sideways. I think there's a way to turn this, but I don't see it pop up here. Usually something comes up here and allows me to turn. I don't know why it did this. Right click, rotate clockwise. Ah, look at that. You're good. Okay, thank you. I knew there was some way to do it. All right. Oh, there was the no. Where are we now? Oh, this thing's doing weird stuff. Okay. Now there was the analemma here. Yeah. Okay. So now we're really not going to use this very much, but this figure illustrates how the equator to the ecliptic angle affects the sun's timekeeping. I don't find all that useful, so you can read it to your heart's content. Here's the important thing. The spin axis of the Earth is inclined 23.5 degrees to the plane of its orbit. So 23.5 degrees in late June, that's the sun 23.5 degrees north of the equator. Late December, 23.5 degrees south. Let's go back here. I hate to do this, but I'm going to do it anyway. I think you can sort of see that here on this. See right here, 22 degrees, 23 degrees, 23.5. That's the farthest north it gets, right around June 21st or somewhere in there. Okay, 23.5 degrees, there's 22 degrees, 24 degrees, 23, 23.5 is right in here, and that's as far south, and that's right around December 21st or so. But you see it's really flat here, so there's a lot of days that the sun's not sinking fast or rising fast. Here, several days too, because the days are closer together, but it's still several days right around the 21st of June where it's awfully close to the same 23.5 degrees. So you see, there's that tilt right there. 23.5 degrees north, 23.5 degrees south. Okay, equator right in the middle of it. Okay. So that just re-emphasizes what we just had there. Now, because the meridians of right, okay, we talked about if we had done the first lab, right ascension, I don't think we have to worry about that much here. We talked about Johannes Kepler, the planetary laws of motion. We pointed those out before. We don't have to worry about that now. We do know, remember, the perihelion, when we're closest to the sun, that's when the planet moves faster. That's in January. Okay, that's why the days there were further apart, stretched further apart, because the sun was, we were moving faster. Aphelion was on July 7th, and that's why those days were closer together, because we were moving slower there. So the motion of the sun along the ecliptic is faster during the winter months, slower in the summer months. Okay, now here is the next question. Briefly describe the effect of the shape of the analemma, that figure 8 that we just saw, if the ecliptic equator angle were to increase. So it's no longer 23.5 degrees. Let's say it goes to 25. What would be the effect on, or maybe just 24, what would be the effect, on the analemma? it would be stretched north to south. You see, this is going 23.5. If it went to 24, it would be there. If it went to 25, it would be here. But it'd also be stretched down here too. 24, 24.5, 25. Oh no, this is 25 right here. So it would be stretched north to south. This is the analemma. Can't you see it? Okay, I went back a page or two so you could see this. Here's the analemma. I haven't turned it again because I have to go back. The question is on a couple pages from here. Again, these pages without a question on, you don't have to send them back, but you can if you want to. But the question was here, number 3. Remember, number 2 had no answer, had no question. Briefly describe the effect of the shape of the analemma if the ecliptic equator angle were to increase from 23.5 degrees, maybe to 24 or to 25. What would that do to the shape of the analemma? It would stretch it north to south. Does that make sense? Now it would have to go up to 25 or 24. Now it only goes to 23.5. Does that make sense? All right. Now, it says obtain from your instructor the latitude of your location and fill it in below. Okay? Now, I'm going to give you the one for Bessemer because that's where I've always done it. Unfortunately, it won't let me write on this screen. See, I can't write there. I don't think I can. Let me see if I can type there. No, I can't. Okay, so I'm going to go back to the whiteboard and write it for you, but you write it on that place. If you got your thing printed, go to the whiteboard, and that will be our, latitude is at Bessemer, 33 degrees, 23 minutes, 45 seconds. That's pretty precise. Birmingham would be a little further north, depends on where you are. If you're down in Hoover, you'd be a little further south maybe, okay? Maybe something below Hoover, okay? So that's what you write on this blank right here. Okay, right there. 33 degrees, 23 minutes, 45 seconds. That's question 4. But question 4 has a second part too. Determine the altitude over the southern horizon of the intersection of the celestial equator and your local celestial meridian. So this is where we get to what we would have done in the last lab had we had it. So I'm going back to the white page and show you what they're talking about here. So it's determine the altitude over the southern horizon of the intersection of the celestial equator and your local celestial meridian. So this is kind of strange, but it sort of makes sense. So I'm going to clear what we've got here. Okay, I'm going to move Labrina. You're in the way again, Labrina. Okay, I'm just kidding. Okay, now this gives me the maximum that I can do. Now my drawing with this ionizing pen is terrible, so live with me, okay? See if you can put up with me. Now I'm going to try to do it as best I can, so I'm going to start with a horizontal line or as close as I can to it. Okay, this will be our horizon. It's not a horizontal line. Let's clear that. That was supposed to be a horizontal line. Let's go back. Okay. No, what is wrong with my line? Okay. Evidently this thing isn't working. It's supposed to not be a pen. It's supposed to be a... Okay. I'm not going to get a horizontal line, so I'm going to do the best I can. It's going to be ugly. Oh, I knew it was going to be ugly. I don't know why it's not drawing a horizontal line for me today. Or even a straight line. I don't care if it's horizontal, just straight. Let's just imagine that's our horizon. Well, that would put the Earth, and I was going to use a ball up here, but obviously it's not going to let me do that either. Nope, it's not. So I'm going to have to draw the best rendition I can of the Earth. And this is pretty lousy. Oops, that's going to be the Earth. Now here we stand in Bessemer, Alabama. There we stand. A little stick man. Okay. Here is our, okay. By the way, our latitude, here is the angle to the center of the Earth, or the line to the center of the Earth, and here's our celestial equator. Our real equator, right there. And this angle here is our 33 degrees. Let me go to my pen down here. I can write a little bit better with 33 degrees, 23 minutes, and 45 seconds. That's supposed to be about a third of 90 degrees there. I don't know if it is or not. Now let me draw the celestial horizon. And this again is going to really sting. Let's see if using this tool, if I can get that. No, I can't. Okay. This is going to be the celestial sphere. And that's pretty ugly. That's supposed to be a semicircle. It's nowhere close. Okay. Now, celestial equator. Okay. Now, supposedly, if I had drawn this right, due north of, directly overhead, and that's not very vertical, directly overhead, this is awful. This is what we call our zenith. Okay. You can draw a lot better than me. Now, our celestial equator would be this. Oh, that's not right. Oh, my eraser's not coming up either. This is really bad news, folks. Here is the celestial equator. Celestial equator. Okay? And this again, just like this angle was 33, 23, 45, this angle is 33 degrees, 23 minutes, and 45 seconds. Okay. Now, what it asks for, oh, and by the way, if that's our zenith directly overhead, right there, this then is our local meridian. It's going from due north, which is here, to due south, which is here. Celestial equator is there. So where is the celestial equator compared to our southern horizon? Well, the difference between these two is 90 degrees, because this is directly overhead, so that's a 90-degree angle here. So here's what we do. Remember? Now, I think I showed you this before. When we're subtracting, it's far easier not to call it 90 degrees, but to call it 89 degrees, 59 minutes, and 60 seconds. Because 60 seconds makes 1 minute, that would give you 60 minutes. Well, 60 minutes gives you 1 degree. That would give you 90. This makes it easier to subtract. So subtract from that 33 degrees, 23 minutes, and 45 seconds. And it makes all your subtraction pretty easy. This is the only one that requires any borrowing at all. This would be 15 seconds, right? Okay, this would be 36 minutes, and this would be 56 degrees. So there's the answer to that next question. How far above your southern horizon This is your horizon, remember, if I could get my pen to show back up. This is the horizon, this supposedly straight line here. See, we got some ponds and stuff. No, I'm just kidding. Okay, to the celestial equator, that would be this 56 minutes, 56 degrees, 36 minutes, and 15 seconds. Okay, so let's go back here, and that's what you fill in here. Determine the altitude above the southern horizon of the intersection of the celestial equator and your local celestial meridian. That's what we had. That's where you put 56 degrees, 36 minutes, 15 seconds. Am I remembering that right? I hope so. All right. Now, it says use the analemma that we were just looking at before in step 4 to fill in this table. And it says the latitude of Altegard, Norway is plus 70. We'll get to that later. Let's do it for right now. Okay. Now this is supposed to be table 48.1. Typed at 47.1, but I put it 48.1. Okay. February 15th, what's the declination of the sun? Okay. Now, unfortunately, y'all are in the way. Okay. I'm going to try to move you to the other side. Let's see if that will help. Okay, now I can move this. So let's do declination. Let's find the declination of the sun on February 15th. Okay, again, this is sideways. Remember, sorry about that. I could turn it over, but I think we can get it. Okay, February the 15th. There's February. Oh, there's a 15th right there. So we have to go up this line. This would be going sideways if you have it printed. Up this line, up this line, up this line, up this line. What's the declination of the sun? What's exactly in between 12 and 14? Come on, somebody. Are y'all with me?
I'm here. I'm looking.
Okay. 13 degrees. This is declination of the sun. 13 degrees south. Because this is south, that's north. Okay, you see north here. You can't see, you might be able to see south. I can't because, there we go. 13 degrees south. So that's the answer for that first question. 13 degrees south. Declination of the sun, 13 degrees south. Oh, that's not what I wanted. Okay. Okay. Now, I may quit doing this quite as much. So that's where you put that. 13 degrees south. Declination of the sun. So the next question is, what is the noon altitude of the sun at your location on February 15th? Well, let's go back to our drawing. Noon altitude of the sun at, now you remember, what's declination of the sun? 13 degrees south? Is that right? Did you all write it down? Okay. Okay. Now I've got this in the way. Let me see. This is, see, here's number 5, but it has bunches of pieces to it. So this is just this first blank right here, declination of the sun, 13 degrees south. Is that right? Yay or nay? Okay, right. All right, so let's go back to our drawing. And here it was, my ugly, ugly drawing. And I don't think we'll need it over here, so I'm going to leave y'all there. Now, what does that mean? 13 degrees south is where the sun is relative to the celestial equator. we're 13 degrees south of it. So 13 degrees south would be almost this line that I have going up here. Maybe it should need to be a little further, but let's just say it's that. Let's say this here is 13 degrees south. Let me go back to my thing here. 13 degrees south of the celestial equator. That would be where the sun is. That's the sun at noon on the 15th of February. Okay? 13 degrees south. The question said, what was the noon altitude of the sun that day? Well, altitude is how far it is above the southern horizon. Well, this degree here was 56, 36, 15, so we're going to subtract 13 from that because it's 13 degrees south of that. That's pretty easy to subtract. That would be 43 degrees, 36 minutes, and 15 seconds. Okay, y'all got that? 43 degrees, 36 minutes, and 15 seconds. Don't expect me to remember these things. My memory is too short. I'm 69 years old. I can't remember that well. Okay, so I hope y'all have written it down because that's what you put right here. Noon altitude of the sun at your location. February 15th, it only goes up that high. Okay, let's go on and do June 21st. Now we shouldn't have to look at the analemma, but we will. Let's go up and find the analemma. Okay. Whoops. June 20. Oh, which one are you talking about? Okay. I ask y'all to write it down. Say again.
43 degrees, 46 minutes, and 15 seconds was the noon altitude.
Did you understand that? 43 degrees.
46 minutes.
40, no, 36, wasn't it? I'll have to go back and look. And 15 seconds. Okay? All right. I told you I can't remember. 43 degrees. I think it was 36 minutes and 15 seconds. I think that's it. We'll go look in a minute. Okay? That's why I asked you, did everybody write it down? Because I can't keep those in my head. Not anymore. Probably never could. All right. You want to go to June 21st? Woo! First day of summer. Okay, is someone coming in? Let me see if they are. I can't tell. No, I don't see anyone coming in. Okay. Say again?
We're not on June 21st. You're on Alien Guard.
No. We're not doing AltaGuard till later. I have to draw another picture for AltaGuard. We're coming back to June 21st. We're going to do everything where we are, and then we'll come back and do AltaGuard. Because I have to draw a whole new picture. So I don't want to draw a new picture until I have to. So let's go back to June 21st, declination of the sun. Okay? We go to the analemma for that. Now that's the same wherever you are on the globe. Okay, I think someone just left. I'm not going to mess with that now. So let's go June 21st. And my goodness, every time I move. Okay, I think someone just came back. Yeah, Denisha. Let me get her back in. All right. I'm going to have to move James. You're in the way again. You know that? Okay, y'all can't see that, but I can. Oh, he was not. Matthew, move back where you were. Okay, now, here's June 21st. Find it on the analemma. There you are right there. And what's your altitude, the declination on June 21st? You should be able to answer that without looking at this. Where are we there? Somebody answer. And 30 minutes. Remember, we're right in between 23 and 24. Right there. 23:30. That's the tilt of the earth. Well, that's our summer solstice right there. Okay? 23 degrees, 30 minutes. Okay, so we have to scroll back down here. Okay, declination of the sun on June 21st. Now my internet is unstable, so I'm not going to do much for a moment here. Okay, did I break up then? Okay. All right. Declination of the sun, 23 degrees, 30 minutes north of the equator. The noon altitude of the sun at your location. So this is where we go back to our drawing. I hope you can draw better than I can. Okay, so now here's a celestial equator right here. We've got to go 23 degrees and 30 minutes. This is just approximate here. So we're 23 degrees, 30 minutes north of the celestial equator. How far are we above our southern horizon? Okay, our southern horizon was down here somewhere. Okay, it was 56 degrees to here, 56, 36. You see, here we were. That number was 40, the one you were asking about before, 43 degrees, 36 minutes, and 15 seconds. That was the one for February 15th. Okay? That's not halfway up the sky, by the way. See, halfway up the sky would be 45 degrees. So you're not, February 15th, you're not even halfway up the sky at noon. Okay? No wonder it's cold. Okay. Right here, okay, you can't read this. 43 degrees, 36 minutes, 15 seconds. I'm trying to write big. Okay? Now, this one, I'm going to try to draw the sun in here if I can. Here's the sun at noon, and this is on 21 June. Okay? Pretty ugly writing. Okay? Now, how far above the southern horizon? Man, it's way up there. Here was 56, 36, 15, and then you're going to add to that 23, 30, right? Add, not subtract, because this time you're above it, north of it. So I'm going to come over here to do it. 56 degrees, 36 minutes, 15 seconds, plus 23 degrees, 30 minutes. Well, the 15 seconds comes down by itself. We don't even need to keep up with that really, but I will. Here, though, we're adding, this is adding this time, 30 to 36. That would give you 66 minutes. Well, 66 minutes is 1 degree and 6 minutes, right? Because 60 degrees in a minute. So that's the 6 minutes here carry a degree. Then that makes this 57 plus 23 would be, oh, come on now. This is old stuff, right? We are. You add 15 to 0 and you get 15. Add 36 to 30 and you get 66, right? Okay, wait. It's 66. But there's 60 minutes in 1 degree, right? Remember, right here. Okay, so 66 minutes would be 1 degree plus 6 minutes, right? So I write down my 6 minutes here and carry 1 degree. Oh, y'all like this, don't you? Reminds you of grammar school, right? Then 6 and 3 is 9 and 1 is 10. Carry a 1. 5 and 2 is 7 and that 1 makes it 8. 80 degrees. It's almost directly overhead, not quite. A little less than 10 degrees from directly overhead. So that's the noon altitude of the sun where we live in Bessemer, Alabama. Okay? So y'all got it? 80 degrees, 6 minutes and 15 seconds. All right. Can I leave it? Okay. 80 degrees, that's noon altitude of the sun on June 21st. 80 degrees, 6 minutes and 15 seconds. Right? Now, we need to go to October 15th. That puts us back at the analemma. Here we go again, October 15th. Come on, analemma. Sounds like a good southern name. Analemma? Okay, never mind, I didn't say that. Do we see October 15th? Oh, there it is right there, isn't it? Was it October 15th? That looks like it's 8 degrees south of the celestial equator, right? You see it? October 15th, 8 degrees south. Does everybody see that? October 15th, right there, 8 degrees south of the celestial equator. Let me hear from somebody. Yes, okay. All right, good deal. I don't have much of a marker here, but there it is. Okay, so you got that 8 degrees south. So that's what we put here. October 15th, declination of the sun, 8 degrees south. Now we have to go back to our picture, okay, our ugly picture. Y'all should be disagreeing with me. Tell me what a beautiful picture. No, I'm just kidding. 8 degrees south. There's the celestial equator, remember? 8 degrees south is not quite as far as we were in February, but it would see somewhere right about here. So I'm going to try to draw a line there. I don't know which is better, to use my pen here or, whoops. So this would be 8 degrees south of the celestial equator. Well, subtract 8 from your 56, 36, 15. That was your altitude of the celestial equator. Subtract 8 from that. And that would give me 48 degrees, 36 minutes, and 15 seconds. Everybody got that one? So this time you're a little more than halfway up the sky. Not quite, not much, just a little bit. 48 degrees, 36 minutes, and 15 seconds. Does everybody have that? 48 degrees, 36 minutes, 15 seconds. That one right there. 48 degrees, 36 minutes, 15 seconds. That's what we put here. Noon altitude of the sun on October 15th. You got it? 48 degrees, was it 36 minutes, 15 seconds? All right. You got it? All right, let's go to December 22nd on the analemma. I'm pretty sure I'm going to have to move y'all now. Y'all can't see this, but you're right in my way. I can't read it there. Okay, so here you go. Diana, move out of the way. Okay. All right. I'm going to move you over to the right-hand side. Okay. Now, December 22nd. There's the 20th, 21st, 22nd. What does it appear to be our declination of the sun on that day? Come on, y'all ought to be able to know this one without looking at it. One day off or right on the winter solstice. What's the declination of the sun that day? Did someone come back in? Nope, don't have anybody. Come on, someone tell me. What's the declination of the sun on the winter solstice? Right down here. Is anyone with me? What is it? What's the tilt of the earth? Come on. Somebody knows that, I know. I think you all know it, you're just not talking. To me, anyway.
Someone said don't panic. She's typing it up for us.
Oh, okay. Does anyone know? 23.5 degrees. Only it's south of the equator. 23.5 degrees. 23 degrees 30 minutes south of the celestial equator. You see, here's the celestial equator. Oh, I'm on the wrong thing. Celestial equator here, we're south of it now. Down here at 23.5, right there. Okay? So, let's scoot down again. On December 22nd, 23 degrees 30 minutes south of the celestial equator. We always put either north and south or plus and minus, one or the other. Okay, 23:30. So let's go and do the noon altitude of the sun on that day. Okay, go back to our whiteboard. Boy, this is getting messy, isn't it? Okay, we're now 23.5 degrees south of the celestial equator. See, here we're 23.5 degrees north. Now we're going to be 23.5 degrees south. So I'm going to guess it to be somewhere about here. Okay, that's my guess. This is the sun. The day after, no, a couple days before Christmas, the 22nd of December. Right here. 23.5 degrees south. 23 degrees 30 minutes from our 56, 36, 15. So let's go over here and do it. Here's the 56, 36, 15. Let's subtract from that 23 degrees 30 minutes. Okay, subtracting there, that gives me 33 degrees 6 minutes and 15 seconds. There's how high the sun is. It barely gets a third of the way up the sky. That's as high as it gets on December 22nd. That's all, folks. Okay? No, that's not the end of a cartoon show, but yeah, okay. So that's what we put, 33 degrees, 6 minutes, and 15 seconds. That's what we put here. Noon altitude of the sun. There, I'm going to scoot this down so I don't keep bumping into that. Okay, that's what you put here. What was it again? 33 degrees, 6 minutes, and 15 seconds. Is that right? All right. Now we're going to go to Altergard, Norway. Way up there, 70 degrees north. Okay. So let me go back to my whiteboard. And now I've got to start all.
Sorry. Can you spell that word for me?
Okay, I'll go back and let you see it.
That's the problem. I'm struggling.
You can't see it? Is that what you're saying? You can't see my screen? Okay, what were you saying?
I'm sure it's just my eyes. I'm just struggling to read it.
Okay.
What
A-L-T,
kind of
okay. Altengard. It's a Norwegian word. Again, it's down here. Altengard. Yeah, I know if you're reading this on a phone, that's going to be hard to read. I understand that. I'm just assuming everybody's reading it from a screen. You may not have a computer screen. If you're on a phone, I understand. But it really doesn't matter. It's on your lab. It's on the lab sheet. Altegard. I don't even know if I'm pronouncing it right. Altengard, Norway. Okay. And it's 70 degrees north is its latitude. So now we got to go back and I've got to draw everything again. Now, yeah. So I think I'm going to clear the screen. Is that okay? Anyone need any of these numbers any longer? Okay. I'm sorry, I wasn't thinking. Y'all are probably reading off a phone, some of you. That is hard to read. I mean, I have trouble even punching the buttons on the phone because my fingers are too fat. Okay, so let me clear the drawing and I'll try to draw another one. Okay, I'm pretty sure it's not going to give me my line again. Okay, so I'm going to try to draw a horizontal line again. And this was a joke before. Let me try it on my Wacom and see if I can do any better job. Whoa! Don't do that. Okay, try it on my Wacom. It's a little bit better because I'm left-handed and I can use my left hand on the Wacom. Okay, now I want to get this thing out of the way, but it won't go down. Okay, there it finally went down. So I'm going to try to get the center of the page here, and I'm going to try to draw a globe. That's not too good either. Okay, and here we're going to be in Altergard, Norway, which is really cold, so I'm going to put us in a big woolly coat. Okay, so here we stand. We got a hat on and everything because it's cold there. Now directly overhead is what we call our zenith. Okay, and here is the celestial. Come on, here's the. Quit that! I don't know why it's doing that. Okay, here is our celestial sphere going up to here and coming down somewhere over here. Now, I can't even see over there because Drew is in the way again. Let me move Drew out of the way. Whoa! Everybody disappeared. Drew, what do you do to them? Okay, that actually is better for me. So, no, quit doing that. Hey, I didn't know I could do that. I can widen my screen. Wow! Now let me widen my celestial sphere and go to here. Okay, wish I could take that out, but I'm not going to worry about it now. Okay, now this dude, us on Altergard, Norway, are at an angle latitude of 70 degrees. That means there's the equator right there. Man, that's 70 degrees. 70 degrees north of the equator. That puts the celestial equator right here. Okay? Which means this is our 70 degrees. That's our latitude. I think my internet connection is unstable. Was I breaking up then? Can you hear me okay? Okay, good. All right. Now what does that leave this to be? What is the celestial equator over the southern horizon? If that's 70 degrees, what would this be? Remember, this is a right angle here, 90 degrees. So what would that leave this to be? 20 degrees, you're right. There's the celestial equator right there at 20 degrees. Okay? Now, we're going back to here. We already have the declination of the sun. Now, I couldn't write it in because it wouldn't let me. But you have it written in, don't you? February 15th, what's the declination of the sun?
13 degrees south.
13 degrees south. So let's go back to our figure on the whiteboard and do 13 degrees south of the celestial equator. 13 degrees south of this, there's the sun on February 15th at noon. That's as high as it gets, folks. How high is that above the southern horizon? This is 20, that's 13, 7 degrees. That's all she wrote, folks. 7 degrees above the southern horizon. So that's what we write here for Altagarde, Norway. On February 15th, 7 degrees above the southern horizon. That's all. Okay. Everybody got it? Okay. June the 21st. Okay. What was the declination of the sun? You ought to know this one without reading it.
23 degrees and 30 minutes.
Absolutely. 23 degrees, 30 minutes north. So that's what we're going to go north of the celestial equator for Altagarde, Norway. So we'll go another 23 degrees and 30 minutes north. Something like this. 23 degrees and 30 minutes north of the celestial equator. This is the sun on summer solstice, the highest it ever gets, 21 June. And how high is that above the southern horizon? 20 and 23? 43.5 degrees. 43 degrees, 30 minutes. That's all it gets. It doesn't even get halfway up the sky on the highest it ever gets in the whole year. That's it. No wonder they're cold up there. No wonder you got on a full coat and a hat. Okay, it's cold up there. 43 degrees and 30 minutes. That's what we put here in June 21st, Altagarde, Norway. Everybody got it? 43 degrees, 30 minutes. Can someone remind me what declination of the sun was on October the 15th? 8 degrees south of the celestial equator. So let's go and put that on our drawing. 8 degrees south of the celestial equator. Okay, that's going to put me somewhere about here. 8 degrees south of the celestial equator. And the celestial equator is at 20 degrees, so what does that put the noon altitude of the sun? Anybody?
28
Say
degrees.
again? No, no, this is south of the celestial equator. 12 degrees. Yes, you subtract 8 from 20. 12 degrees is how high it is. That's as high as it gets on October the 15th. It's only 12 degrees. Boy, I don't want to go trick-or-treating there. Okay, that's, well, you could go pretty early in the afternoon when the sun goes down. Okay, that's a different story. So everybody got that? 12 degrees. That's what we put here. October 15th, noon altitude of the sun, only 12 degrees up there. Just barely. Okay, December 22nd, what was the declination of the sun? Boy, you all 30 minutes
30 minutes
south. Exactly. That's what I was looking for, south. Okay. Let's go here and see what happens if we try to draw that in here. Here's a celestial equator at 20 degrees. 23 degrees would be somewhere down here. Where is that?
south.
Yeah, don't even mess with it. It never rises. The sun you never see. That's north of the Arctic Circle. Arctic Circle's at 6630, I believe it is. This is 70. Hey, you don't see the sun all day long. You waiting for morning to come so you can get up and open your Christmas present? The sun never rises. Okay. You don't get any. No, I'm just kidding. The sun doesn't rise. The sun, the highest it gets is below the horizon. Now, I bet you get a little bit of dawn type feeling, but you know when that would be? Right around noon. The sky will get just a little bit lighter. You'll never see the sun, but then probably by 1 o'clock it's dark again. Okay. Never saw the sun. That that would be perfectly okay. If you really are insistent, you could put, no, I mean, noon altitude of the sun, it it's not even visible. You know, whatever you want to put there, it doesn't rise. You don't have, you don't see the sun on noon, at noon, on the 22nd of December. In fact, there's probably several days there you don't see the sun. Like I said, right around noon it might be getting a little lighter, but you still will not see the sun. It never rises. All right, we beat that one into the ground, didn't we? All right, now here's the next one. Number 6. Rip Van Winkle awakens from his extended slumber and asks a passerby what year it is so he can determine how long he slept. The passerby quickly responds and rapidly moves away. I mean, this guy, he's been sleeping there, what? Anyone remember how many years it was? 20 years. I have a feeling he may have been pretty right by then, okay? So anyway, this is all fiction, by the way. Realizing a 20-year snooze might be a new world record, yeah, I think so, he thinks he should pin down the date as well as the year. He just knows what year it is, but he didn't ask the guy what day it was. So he moves out from under that tree where he slept for 20 years. He must have been really tired. And measures the altitude of the sun above when it crosses his local meridian. He finds that to be 44 degrees over the southern horizon. So let's go to our whiteboard and we're going to draw that. Okay, so let me erase this again. Okay, now going to try again to draw my horizontal line here. It's supposed to be a horizontal line, not a very good one. Okay, here's Rip Van Winkle's Earth here. Now we don't know where he is yet, so we can't put him there, but we will draw him here. He's a cranky old guy with a very long gray beard. because he'd been sleeping for 20 years and hasn't shaved. Okay, so there's his ugly beard. I'm going to put a hat on him too because he slept in the winter time too. All right, let's do the best we can. Let's draw his zenith first. That seems to be a good thing to draw. Directly overhead is his zenith. Okay, and we'll draw the, whoa, don't do that. What is it doing here? Okay, I don't know what this is doing. You can see this again, catch it. Okay, let me scoot this back out. Okay, I'm trying to pick up the northern horizon here. There we go. Okay, given a few years I might be able to do this. Okay, now what did he notice? He noticed the sun was 44 degrees above his southern horizon. Let's just say this is 44 degrees. It looks like it's a little less than that, but we'll live with it, okay? So, remember, this, by the way, is the southern horizon. This is the northern horizon. Okay, now, all right. He finds it to be 44 degrees above the southern horizon. He knows that the latitude of his chosen spot on the Hudson River in New York State was 42 degrees. Now 42 degrees is his latitude. So let's go back and draw the latitude in. All right, latitude is how far he is above his equator. So we're going to draw the line down here, and 42 degrees would be something like this. So there's the 42 degrees. That's from due north, is zenith. So 42 degrees here would be something like this. So this is his 42 degrees. Now again, my drawing is not very precise. Okay? That means this is the celestial equator, because that's how far his latitude is, how far above our equator it is, so his zenith will be how far it is above the celestial equator. Okay, that's on the celestial sphere. That's his local meridian. Okay, let's go back and see what else we know. Okay, he knows the chosen spot. On what two possible dates could Rip Van Winkle have awakened? Now, how do you get dates out of this? Or figs or anything else? Okay, let's see what we can figure out. If this is the celestial meridian, and this happens to be the sun at noon on whatever day he arose, then we know, okay, let's do this. If this is 42 degrees, what would this be? 42 from 90 would be 48, right? 48 degrees, because 48 and 42. What's this? Oh, come on, this is just subtraction. Okay, if you need to do it over here. 90 degrees minus 42, because that's how far you are below that. Okay, you have to borrow one here, make this an 8, make this a 10. 2 from 10 is 8, and 4 from 8 is 4. 48 degrees. That's how far the celestial horizon is from above the southern horizon. So that makes the sun here. So what would be the declination of the sun here? If this is 48 degrees here, this is 44 degrees here, what would be the declination of the sun? 48 to here, 44 to here. What's the difference here? Come on. 4 degrees south of the celestial equator. So we go to our analemma. Good old analemma. She was a good old gal, wasn't she? Okay. Let's go to analemma here. 4 degrees south. Okay, there we are. 4 degrees south is right there. You see it? Right under the E of declination. You see it? Or, okay, let's go south. Okay, let's make that maybe the 4th day in October. So it's either October the 4th or, come on down the analemma here, and that looks like maybe the 11th of March. What did I say? The 4th of October or the 11th of March. Okay, is this somebody else coming in? Okay. So, did y'all get those? Did someone write that down? Okay, yeah, 4th of October or 11th of March. Oh, almost went past them. Okay. So there's the first question. On what 2 possible dates could Rick Van Winkle have awakened? What did we say? 4th of October or the 11th of March? You got them both?
Yes, sir.
Now, he notices that the buds are just appearing on the tree he slept under. So what day you reckon that would be? March 11th. Got it. Okay. Now, so let's go back. That finishes question 6. Question 7. As we saw previously, the analemma graphs the daily difference between clock noon and apparent noon when the sun crosses the meridian. As an example, check the analemma in figure 48.4. They keep changing all these figures. 48.4 to see that on October 15th, we were just there, close to it, the sun will cross the meridian 14 minutes before clock noon. So let's go back and look at it. October 15th, they say is 14 minutes before clock noon. So let's go and find it. October 15th. Okay, here's October 15th, right, where is my, there it is. There's October 15th right there. You see it? And let's see how long before clock noon that is. Move along this line, there it is, 14 minutes before clock noon. So anything up here is before clock noon, anywhere back here is after clock noon. Before on the upper side, after on the lower side. If they're standing upright, before would be to the left and after would be to the right. You got it? Okay. Okay. We were told that on October 15th, there's October 15th, you see it right there, on the analemma, we were 14 minutes before clock noon. There's the 14 minutes right there. And on this side of, this is clock noon, 14 minutes before clock noon. Over here would be so many minutes after clock noon. Okay? On this side is before, this side is after. Got it? Okay. Now, let's go back and see the rest of our question. Okay. Yeah, there was what we just saw. Saw that on October 15th, the sun will cross the meridian 14 minutes before clock noon. So for the dates in the table listed below, use the analemma in figure 48.3, they got it right this time, to determine whether the actual sun will cross the meridian before or after clock noon. So this column right here, this column here, all you write is before or after. Before or after. That's all you write here. Then over in the third column, that's where you write how many minutes. Before or after here, just the words. Before or after, over here, how many minutes. So let's start with January 10th. Okay, let's come up here and find January 10th. Oh, I think I see January 10th right there. You see it? January 10th is right there. Now, I don't know which side it's on. Sort of hard to tell. I think it's right there. So let's move up. Okay, first question, are we before or after clock noon? We're after. So in the first column, you write after. In the second column, how many minutes? Can anyone see my... Say again? I think this is 6, that's 8. So I would say 7, wouldn't you? Yeah, because there's 4, 6, 8. So call it 7 minutes. After 7 minutes. Okay? Everybody got that? Okay. January 10th. In this column, after. In this column, 7 minutes. Let's go to February 15th. February 15th. Let's see if we can... Oh, there's February right there. And 15th's right about there. So let's scoot the line up here. First, are we before or after? First answer for before or after. Anybody? After. How many minutes? Anyone? That's a 14. Yeah, that's a 14. Y'all must be reading from a phone because it's pretty clear on my end, but yeah, I understand. So after 14 minutes. Okay, that's February 10th, wasn't it? Say again? Yeah, no, February 15th. February 15th. Okay, now we go to April 15th. That used to be text day, but recently it hasn't been. April 15th, let's see. First we're going to say before or after, and then how many minutes. April 15th. Let's see if we can find April 15th. There's March. Here's April. Here's April. Oh, 15. Goodness gracious. Is that before or after? No, I think it's April 15th. If it's right there, which I think it is, just a little bit below it, so that would be on the after side. But it's not much. I would just say a few seconds. It's not even close to a minute. So it's after by only a few seconds. Would y'all buy that? If you want to say right on it, you could, but you know, it looks like it might be after by just a few seconds. April 15th, after, not much after, just a few seconds. Amount of time before or after clock noon, just a few seconds after clock noon. You're awfully close to right on the money that day. All right, how about July 30th? Ready to go? Okay, July 30th.